All right, so it seems like people are slowly trickling into the Zoom webinar. So we should get started so that we can be on time. Welcome everybody to the 3DReps workshop, or welcome back if you attended session 1 already. This is session 2 of the 3DReps workshop. Before I begin, I just want to make sure that everyone can hear me fine and can see the slides on the screen.
Yeah, we can hear and see.
Okay, thanks, Or. All right, so yeah, welcome to session 2 of the 3DReps workshop. My name is Srinath, and I'm joined by my co-host, Or. Before we dive into the today's program, I wanted to do a recap of session 1. So in session 1 of the 3DReps workshop, we had 3 great invited talks by Tom Funkhauser, Christian Grauman, and Angju Kanazawa. So this was in session 1, which was held 16 hours before. We also had a great lineup of 14 invited posters who presented their posters in an interactive session using a tool called gather.town. And I'll be talking a little bit more about their experience in a couple of minutes. Moving on to today's program, this session's program, we have 4 more exciting invited speakers that'll be speaking today: Angela Dai, Jitendra Malik, Niloy Mitra, and Noah Snavely. And a subset of our invited speakers will also participate in a panel discussion, which will be hosted by Gordon Wittstein. As usual, please go to our website, the link of which you can see in the top of my screen share, to get the latest updates and to see the schedule of the talks for today in your local time zone. So please visit the website for most up-to-date information. And finally, a quick note on the interactive part of the workshop. As I said, we've been using this tool called gather.town in order to have an interactive space where we can simulate some of the experiences of being in an in-person workshop. I believe Or just posted a link to it on the chat window. Please feel free to hang out. We are going to keep this session open. Please feel free to hang out in that interactive session. It's a nice way to interact with your fellow workshop attendees, other researchers presenting posters, and perhaps also the invited speakers. And a very quick fun thing that happened after the first session yesterday was that a subset of us were hanging out post the workshop to grab some drinks or some kind of social event. So I hope to see many of you there after this session of the workshop as well. Or did you want to add something about gather.town?
No, but I'm getting some very positive feedbacks from you, and some have sent me emails with some suggestions for future ideas. Some of them we can implement, some of them we'll have to pass forward to gather.town, the company, so they can include that in their platform. But all in all, I think the experience was good, and I also saw many people hanging out there, even way past the workshop hours. And just so you know, this is open today throughout the workshop as well, so make use of it.
All right, great. So yeah, with those logistical information out of the way, let's begin session 2's program. Let me stop sharing my screen. Okay. All right, so as I said, we are going to start with our invited speaker. And our first invited speaker for today is Angela Dai. Angela Dai is an assistant professor at the Technical University of Munich. Her research focuses on understanding how the 3D world around us can be modeled and semantically understood. Previously, she received her PhD in computer science from Stanford in 2018 and her BSc in computer science from Princeton in 2013. Her research has been recognized through a ZDB Junior Research Group Award, an ACM SIGGRAPH Outstanding Doctoral Dissertation Honorable Mention, as well as a Stanford Graduate Fellowship. Today, she'll be talking about self-supervision for 3D scene generation from RGBD scans. It's my great pleasure to welcome Angela. Angela, the stage is all yours. And just as a reminder, I will be giving you a 5-minute reminder at the 20-minute mark, just so you know. But other than that, the stage is all yours. We look forward to your talk.
Thanks for the great introduction. So yeah, today I'll be talking about self-supervision for 3D scene generation. And I think what we're all interested in this workshop is sort of how to create 3D representations of objects and of scenes. And what I'm interested in particular is capturing actually real world environments around us. So from a commodity sensor device that is able to image these environments, how can we capture the 3D representation of these environments that are around us? And so this has a lot of potential applications for things like immersive applications of mixed reality, being able to mix virtual and real environments, as well as applications like autonomous navigation, exploration for robots to move around and to explore and interact with the environments. And so one particularly promising avenue towards capturing these 3D reconstructions of these scenes, these real world environments around us, is basically with reconstruction from these commodity RGBD sensors. So here you have a Kinect camera and you can see the color stream, as well as the depth stream, which is measuring the depth corresponding to the color images, and optimizing for the frame alignment between all of these frames in the video lets us reconstruct a 3D model of the observations here. And so here you can see one of these 3D reconstruction systems live in action. And this is basically optimizing for the frames and producing this 3D reconstruction here that is represented in a volumetric grid as a truncated sign distance field. And so this is a sparse volumetric grid that's storing the scene representation here and is being updated on the fly according to the computed camera poses. So the kind of reconstruction that we can get out of this system, here you can see one example. And so one question would be, why don't we use basically 3D reconstruction from these commodity devices to as the main approach for 3D capture for all these nice applications? And there are a few challenges here in terms of the reconstructions that we can achieve. So one big challenge here, we can see when we turn this particular reconstruction around. So here you can see from the top, it's you can identify pretty much all of the major objects that are in the scene. But when we move it to a different view, we see that in fact, there's actually quite a bit of missing geometry from the room. And part of this is due to just not observing enough, but the other regions are practically impossible to capture here. A lot of occlusions in the scene because this is a reasonably cluttered, complex scene, and the physical sensor, it has a size, so you cannot move it everywhere to be able to capture all of the geometry. And there are some other difficulties in terms of like sensors being light-based can have some trouble capturing regions like the chair legs that are often metallic or very thin. So we have this issue that we want to be able to infer the complete scan geometry from these observations. So how can we learn to generate complete scene geometry? So one approach is to leverage some of these recent advances in 3D generative learning, deep learning. And we want to treat this as a traditional kind of supervised problem where we have input target pairs of incomplete scenes and complete scenes. So now that I've just mentioned that it's actually practically impossible to capture a lot of real world scenes with complete geometry. So how are we going to actually get the ground truth for this particular task? So one approach is basically to take a look at synthetic data, of which there are increasingly more in terms of synthetic 3D data that's available. So we can leverage a synthetic database where we have actually all of the complete geometry and use that for the target complete scenes. So here you can see that we've processed this data actually into the same kind of representation as the scan. So this is actually the isosurface of the TSDF that's being visualized here from this particular synthetic scene. And in order to generate the counterpart incomplete pair, we can simulate the scanning process by virtually imaging the scene and fusing it together in the same way that we reconstructed the 3D scan. So here we've taken a camera and moved it around this particular scene. And now we can actually create some incomplete pairs of scanned TSDFs where we have a ground truth pairing of incomplete and complete data. So now we can tackle this problem by developing a generative network in order to fill in these missing regions. So the approach that we took here was basically to have a voxel-based approach, since this is a voxel-based TSDF representation. And we're fully convolutional so that we can actually handle the arbitrary sort of sizes of test scenes, since rooms and objects and scenes can all be of varying sizes in 3D. So we can operate on a single test input in one forward pass. And in order to account for these kinds of different levels of detail, we also have a coarse-defined hierarchy here. So here we predict very coarse level complete geometry first and continually refine it into the finer levels. And so you can see the kind of completion results here in terms of the geometry from an input virtual scan of the synthetic data with the ground truth on the right-hand side. And here it's able to capture a fair amount of both larger level structural elements like walls and floors, as well as finer grain detail on chairs and tables. Here you can see this particularly incomplete region because it was seen basically from the back of the chairs. And here the full chairs are generated through this process. And so this is a nice tool in order to be able to produce geometric inference for the complete scans from these kinds of partial observations. So here you can see, in comparison to some traditional optimization approaches like Poisson surface reconstruction, as well as some prior learned approaches, this in particular, this like coarse-defined processing and this fully convolutional nature enables a pretty accurate geometric completion, but this is also evaluated on synthetic data. And the real kind of application that we were taking a look at the beginning is in terms of how can we infer the complete geometry of a real world scan. So if we apply the same kind of approach to real scans, so this is scans from the ScanNet data set, and this is operating at around 5 centimeter voxels because it's operating in a dense voxel grid. So here you can see the completion results for the geometry on the bottom. And while it's not super unreasonable, you can see that there is an effect in this domain gap between synthetic data that was being trained on and real data that we're now testing on. So here we have a lot more sort of bumpiness in data, especially like the walls and the floors. And the objects are not arranged so perfectly, and we get also a bit of this out now in the completion results. So how can we really learn to generate the geometry of real world kind of scan data? So what I want to propose is a self-supervised approach toward this particular problem. So an RGBD scan is composed of a set of depth frame observations. So these ones we have many of them available in data sets like ScanNet and Matterport. In this case, we have these depth frames reconstructed together into a target scan. This is from the Matterport data set, and you can see, it's relatively complete, but it's still missing some regions. And now this is the most complete kind of scan we have available, so we want to use this as target and instead create a more incomplete version of it for the input. And so here we remove a few of the depth frames and create the corresponding input scan. So now we have this pair between more incomplete and less incomplete version of a scan. And so we can try to learn what is the sort of generative process between the more incomplete to the less incomplete one. So here we want to take care that we actually are not considering regions in the target scan that are unknown or unobserved. So these are these particular regions that we've marked here. These basically haven't been seen by the camera. And since we've reconstructed this from the depth frames and the camera trajectory, we know actually which regions have not been seen from the camera's point of view. And so we want to ignore these during the training process. So now we can set up this self-supervision between a more incomplete scan and a target scan while ignoring all of this unobserved space. So also in particular here, we want to be able to generate somewhat higher resolution kind of geometry than previously at like 5 centimeter voxels. So instead we take a sparse voxel representation here. So this is a TSDF still, but it's not being stored in a dense volumetric grid. Now we store in a sparse volumetric grid. So we only need to store the voxels that are actually near the surface. And that lets us get up to a higher resolution in a more memory efficient way. So here we have an encoder that operates sparsely on these voxels, and then we spatially downsample until we can make a very coarse dense prediction. So then we are able to sort of create geometry where we haven't necessarily seen it before in the input. And then we continually prediction upsample and refine in this kind of coarse defined way, progressively generating the final output. So here every upsampling is by a factor of 2. And so we finally get up to the predicted geometry here, where every level here is basically predicting which voxels should actually stay as part of this sparse set. So you want to be able to generate also a sparse TSDF as output. And then we can actually produce this high resolution complete geometry. So here you can see an example of an input scan, the completion, as well as the corresponding target scan that was also more complete in this particular test set. So the nice thing about this particular approach is that because we're ignoring all of this unobserved space in the targets, we can actually generate complete geometry that is more complete than any single train scan that we've seen, because we're learning to generalize across many different examples of partialness in the data set. So we can learn to generate something that might be more complete than the target scan. So here we have an evaluation. This is, again, against the prior approaches of an L1 error on the voxels in terms of basically all of these approaches, except for Poisson surface reconstruction, which is not trained, they're trained in a fully supervised fashion. So if we need to train them basically on synthetic data and apply it to real data, and here you can see that our approach is noticeably outperforming this in terms of actually being trained on a far more limited set of real world scans. So here you can see like the effect of this like unobserved masking and the loss. So, what if we just took the same kind of approach where we didn't bother to ignore the unobserved regions? So here you can see in the second column basically that then we learn also to generate similar patterns in terms of this incompleteness in the final results, because they were there also in the targets. So this kind of self-supervision masking in the loss is important in terms of really generalizing it and learning actually how to produce these complete geometry. And another nice thing about this kind of approach towards self-supervised scene generation is basically that we don't necessarily have to use as complete of target data as possible during training. So if the real world scan data set happens to be less complete than the set of targets that you see here, which are in fact relatively complete, we can train on actually a subset of the frames in the target scans to simulate this kind of more incomplete target data. And here we have 3 different versions. So basically on the bottom, we have 50% of frames used for input and all frames available for target. And then we have 40% for input and 60% for the target. And then 30% for the input and 50% for the target. And if you do see that the performance drops a bit as the target training scenes become more incomplete, but it's relatively robust to the incompleteness of these target scans that are actually used for training. So that's kind of a nice property in terms of this approach towards self-supervision and generating this geometry. But so now we have the ability to create these scenes in terms of geometry, but we also want to be able to, get colors, because, for many kind of applications, we want to actually know not just about the geometry, but about the color of the scenes here. So we want to adapt this in order to generate a colored scene. So of course, a natural approach here is to just add color now into the standard kind of formulation that we have, and see how this goes. The problem is, for color prediction, this isn't quite enough to get the nice kind of results you might want to have. And the reality is, if we use basically this kind of L1 reconstruction loss on a color, and we work on indoor scenes, which are largely composed of walls, floors, and ceilings, you end up with colors that are basically beige, which is the color of the average wall, floor, and ceiling. So what we want to do instead is actually have a view-guided synthesis here. So we want to basically predict still a 3D scene, but the supervision now comes from every single view compared to the original observed views. And this has also the advantage that every view here now is actually complete from that particular view. So you aren't missing colors, you aren't missing geometry from that particular view. So you can actually use this to train to generate actually a complete geometry and color. So here you can see we've generated the scene, and then we render views from this particular scene that we've generated, and now we can compare it to the target views. So here we have a reconstruction loss for both the geometry and the color. This is an L1 loss. And we can also adapt some of the tools from a lot of the successful 2D generative approaches, which is perceptual loss here, as well as an adversarial loss. And so that lets us better learn this kind of color distribution of the data and what's actually realistic colors to predict. So here you can see an example of the input incomplete observation here. And if we use just the reconstruction loss, we end up with pretty washed out, blurry kind of results. If we now add on a perceptual loss, we actually get a fair bit in terms of detail, but it's not quite enough to fully recover from the sort of data imbalance, and still tends to wash out quite a bit. And now if we add this adversarial loss, we can start to see the original color distribution come back. So when we combine them all together, then we end up getting the sort of prediction that is reflecting now what we might expect to see as a realistic kind of colored scene based on the input observations. So we can also evaluate the kind of effect of this colored scene generation by taking the FID score of just render views of the predicted scenes. So this, it does evaluate to somewhat high kind of numbers. This is also because of a we don't have a fully complete like rendering out as output, and it's being rendered from voxels. So it's not quite the same as if you would take FID scores from like standard images to images. But here you can see that in this case, we're able to achieve a more sort of realistic prediction with respect to the FID score. And you can see also that the visualization here shows that from these kind of incomplete observations, this kind of 2D supervision, this view-guided supervision allows the generation of complete color and geometry here at the same time.
Angie, sorry to interrupt. Just this is your 5-minute notice.
Thanks. Yeah, so here you can see an example scene of the partial observation and the final prediction. So what comes next from this kind of stuff? I think I've talked a bit more about kind of how to learn to generate 3D scenes, and a little bit less in terms of the actual 3D representations themselves. So the representations, of course, are still important to explore in this regard in terms, especially with respect to color generation, whether you want also the color to exist at the same resolution as the geometry, which is something that a mesh and a texture have the ability to sort of decouple these resolutions to some degree. And then, of course, this like possibilities with implicit representations in order to get really even finer grained detail potentially than sparse voxel grids. And I think in terms of this formulation where we have also supervision from 2D images, this also has a strong correlation to a lot of recent work in terms of neural rendering, where we want to be able to actually generate photorealistic images actually as output as well. So that's, I think, also pretty interesting to couple these together to really generalize to full scene kind of extrapolation and synthesis of both the 3D scene itself and synthesized views. So yeah, with that, I'd like to conclude, and also thanks to Srinath and Orr for inviting me and hosting the workshop. And I'm also happy to take any questions.
Thank you so much for the great talk, Angie. So just as a reminder to our attendees, if you want to ask a question to our speaker, please type your question in the Q&A box. And we already have one question in the Q&A box from Andrea Tagliasacchi. Andrea asks, what's your take on the convergence of methods like surface reconstruction or scans and differentiable rendering like NERF? Do you think the latter will eventually absorb the former? And if not, why?
I mean, I think that they're both important in some ways. So I'm taking that kind of, maybe you can correct me if I'm wrong, as a question about kind of implicit representations versus explicit representations. And I think the convergence of the two together is pretty promising, but there are a lot of interesting questions here, right? Like implicit representations so far do tend to struggle a bit more in terms of larger extrapolation tasks. So like, you know, moving, for instance, with NERF, the camera very far from the trained set of views or to generalizing to very large kind of scale scenes, there's a bit more struggle there. And that's something that I think these kinds of more traditional approaches, it's certainly not that they generalize super well, but they do seem to be able to extrapolate towards more general patterns. We have also the advantage of things like translational invariance with convolutions. So like kind of combining them together does seem to be pretty promising. I also wonder how much you can take from these observations in terms of activation functions in implicit representations and this kind of work and pull it back to more traditional convolutions. But I think that's, we have to see what comes.
Great, thanks for that. We have one more question from Alexander Safin. Alexander asks, thanks for the talk. How your approach will work with noisy and sparse data like time of flight or bad sensors? And what could you suggest to tackle unknown degradation of input depth? And I think just to add to that, I have a similar question as well. So in your simulation, how far do you go in modeling the sensor noise when you gather the data?
Mm-hmm. Yeah, all very good questions. So in terms of, noisy and data, generally speaking, degradation, there's obviously, like, you would like to have enough of the data that you would like to operate on to be able to fine tune it if there is something available in the data set. Because if the data that you're training on in a self-supervised way is noisy to begin with, then it's also going to appear in the target itself. So that, funny enough, can be regularized away to some degree by the coarseness of the resolution. So if you operate at relatively coarse resolutions, it actually helps to smooth away a lot of these issues. But of course, once you get to something that's very fine detail, then you'll see that start to show up in the actual reconstructions. And I think that there's something that can be done there in terms of perhaps not actually moving somewhat more away from the depth in the supervision and towards largely color supervision, since color images are far from perfect, but they're usually better quality than the depth ones. I mean, in terms of very, very sparse data like LiDAR scans and stuff like this, I think the general principle can still hold, and I think it would be pretty interesting to see what happens there. But of course, then it's also a bit of a question about the representation that is able to have enough level of detail, but also spanning something that is really city scale. In terms of simulating the noise in the synthetic case, that's not something that we put too much effort into. It can definitely have been more realistic in terms of the sensor noise, since we do now have, I think, a fair number of work on camera models themselves. So like, instead of just adding a bit of Gaussian noise to the data, or like the camera trajectory simulation itself is also somewhat naive in terms of just sampling camera statistics from real world scans. So both of those could be improved in terms of simulating more realistic like noise patterns. But I think you'll still get a little bit stuck at the moment in terms of synthetic data with respect to kind of the global structures of the environments are very clearly synthetic. But yeah, you can probably bridge the gap a little bit more than with a more realistic kind of simulation of real world data capture.
Great, that makes sense. All right, so we do have more questions, but I encourage these questions. Maybe we can move some of these questions to the panel since we are running a little bit short on time. But Angie, thanks again for your talk and for answering our questions. I'd like to hand it over now to Or, who's going to introduce our next speaker.
Thanks again, Angie, for the very interesting talk. And Angie will also join us in the panel later, so don't go too far. And you'll have more chances to interact with her. So she's around. I'm very honored to introduce our next speaker, Professor Niloy Mitra. Niloy, maybe you can share your video just to say hi to everyone? Niloy is here with us.
I cannot share my video. It says I do not have permission, but I am around here. I would resolve it.
Okay, I'm sorry about that. So Niloy has prepared a pre-recorded talk, but as everyone can hear, he's around. So we will take Q&As. We will take questions at the end of Niloy's talk. So a little bit about Professor Niloy Mitra. He's a professor of geometry processing in the Department of Computer Science at the University College London, UCL. His research interests include shape analysis, computational design and fabrication, and geometry processing. Niloy receives the 2013 ACM SIGGRAPH Significant New Researcher Award, the BCS Roger Needham Award, and the Eurographics Outstanding Technical Contribution Award. And he'll be telling us today about controllable content creation from unlabeled data. Niloy, the stage is yours. I will not give you a 20-minute mark heads up because I know your talk takes 31 minutes exactly. So we'll play the video and we'll reconvene for the questions afterwards. So.
Hello, welcome. I'm Niloy Mitra from University College London and Adobe Research. Today I'll be talking about controllable content creation from unlabeled data. Now, let me start by showing you some state of the art in terms of what we can achieve if we have enough supervision. So this is reconstruction of an area near my office in London, showing both geometric reconstruction, both in terms of synthesis of elements like balconies, windows, and roof structures, along with the associated texture that is learned from facade images, along with semantic maps that we extract from this. So we have seen here and many other similar efforts that with enough supervision, whether in the form of 2D data or 3D point cloud or meshes, we can get very plausible and realistic looking outputs, whether in the form of geometry or in the form of material. What I'm going to talk about today is a bit different from that. We are going to see like how much can we achieve the similar type of results and controls if we do not have annotated data. If we have data but without specific annotation about semantics, about material, about texture, what can we do without them? So I will talk about three works that we have done in the last couple of years, going from images to image sequences and also object level controls. And these are done in collaboration with students, Philip, Tu, and Sebastian, and other collaborators, as I will explain. So let me start with a very classical philosophical question, which starts with Plato's cave, where if all we have is observations of the world in the form of images, that's all we can see, what can we tell about the world, about the 3D world in this instance? So this is a very classical and old problem. The twist we introduce here is, although we have only 2D observations, in this work we are going to assume that we know the image formation models, like how a 3D object, in this case as you see here, the objects behind the wall gets projected onto the cave wall under illumination, in this case the source of fire as you see here. However, in this work, we are not assuming that we have access to the direct 3D world. We have only access to the supervision in terms of the projected images. So this is what we presented at ECCV last year. As I mentioned, we will be heavily using the rendering equation or the image formation model. Now, as a quick overview of this image formation model, it relies on having access to a 3D model, along with from where we are seeing it, this is the camera angle, and then the material associated at each voxel in the form of color, illumination, etc., like whether it's an emittive source or not. And taking this all together, we have an image formation model that produces images. Right? In computer graphics, over the last few decades, we have developed models for these image formation with various complexity. In this work, we are going to make use of these known functions and show how we can use these known functions to structure our learning network so that we can work directly on the images. So the green observations in this case to say something about the 3D model that is not directly observed. So we will study three types of models. The first one is what we call a visual hull, which should be familiar to many of you coming from the vision background, where we are assuming that we have a grid or a voxel grid where each location can be occupied or empty. Occupied will be 1 and empty will be 0. And now if we shoot a ray that goes through a stream of voxels, if all of the cells are 0, that means not occupied, so all the VIs are equal to 0, so then the observation we'll get is 1 minus exponential of 0, which will be 0. Right? So this will be empty or white in this instance. However, as soon as one of the cell is occupied, or VI is equal to 1, then we will get a dark value, and with the sigmoid function, we can make it look black as we have here. Essentially, as soon as one cell is occupied, we would get a dark silhouette image for that location. The next model we will study is what we have, the absorption model, where instead of completely blocking the light, it allows some light to go through, and the amount of light that goes through is 1 minus VI, and then the total amount of light reaching our eye is going to be the product of this, 1 minus the product of this. So that's the absorption only model. And then once we bring in color, we have emission also. So there's a transmission, which is given by the expression in the front, which was essentially the absorption model we had before. But then at each cell, there is a color, which is given by the VEI, which is the color associated at that location or voxel, and that gives the color of the whole object, which is reflected in our eye by the image. Right? So these are known 3 reflection models or image formation models. Okay, so how can we use these models to learn directly from the data being images in this case? So let me explain the pipeline, what's going on. So what we have is an input observation. So that's an image, a single image in this case, that is encoded into some latent vector Z, right? And then from this Z, we are trying to find a generated G that is going to produce an object in 3D, right? In this work, we assume the representation to be a voxel grid where each cell has an associated value. And that value can denote occupancy, can denote absorption, can denote occupancy and an emission coefficient. So these are different models. And then this 3D volume is taken is imaged or projected under a random view direction, because we don't know the camera view, but we know the camera model. So this forms a rendering layer, and that outputs the image. So the whole idea behind this Platonic GAN that we introduce is these images or these projections should look like projections of other objects in the database. So in this case, we have a unstructured collection of chair images, and this rendered image should look very similar to this. And to look similar in the sense that discriminator in a GAN setting cannot tell if it's coming from the source image or the one generated from the pipeline. So now I can stress the main components again. The imaging part, where this voxel is taken and converted to an image, this is a known function and a differentiable function. So that's not what we are asking the network to learn. What we are asking the network to learn is simultaneously learning the E, the encoder, the generator G, and the discriminator, such that the voxels are found out so that the projected image are indistinguishable from the discriminator point of view. And this is trained in a GAN setting where we write down the equation for the explanation I provided. And the pseudocode, if you look at, is exactly doing the same thing. So we encode in the first step, and then the I view is a rendered image, and then there's a discriminator that tries to distinguish between this and the original image. There is one challenge that I will come back to, is this view sampling. Because we don't know the original camera, we have to sample across random views to come across this. Now, this is when we structured this network, we were quite surprised to see that it actually can come up with realistic volumes, although it never sees 3D or never gets direct 3D supervision. It's good to see in context with many of the contemporary work or the works that were done before. Some of the authors are also presenting at today's workshop, is to see the amount of supervision needed by various of the single image to 3D model conversion algorithms. So in our case, we do not expect any annotation. We do not expect access to a 3D template. We do not expect that we know the camera views, and that's a source of complication, as I mentioned. There is not even a predefined set of camera poses where the image is taken from. We are expecting a single image, and we are able to handle color. Right? So it's a quite a difficult setup if you're working in this area. So let's see how far we can go with this type of an approach, where we do not have access to the 3D training data. So in each case, you see a result where the black object is a source image that was given, and the pink voxels are the corresponding views of this aeroplane that has been recovered. And in each row, we are showing two views of the same object or the aeroplane in this instance. It's quite remarkable that we can do this in the sense we never got to see, the network never got to see how a real 3D plane looks like in 3D. And that's why we gave this the Platonic GAN name. So this is the same thing over the set of chairs. In this case, you can see the chair examples are given on the black silhouette lines, and the chair or the sofas are, as we have observed here. And this is on a different class on the gun data set. And again, you can see the fidelity of the output. Okay. In all these cases, we are only working with the occupancy volume. So there's no material associated. The color is just a fictitious color because it's a uniform color throughout. It's an absorption only model that we talked about. So we ran extensive quantitative evaluation to see how far we can go with this unlabeled data set, where the goal is to do image synthesis and then take the 3D volume, do an image synthesis of a target viewpoint, and evaluate the quality of the output using either VGG features or structural similarity as DSSIM. And as you can see, our method works quite favorably if we have 2D data only, and if we have also some amount of 3D data, then it does even better, which we call hours plus 3D. And PRGAN was one of the best performing in this setup before this. Okay. Now, if we have additionally some 3D information available, so there are cases where maybe we have a smaller data set of aeroplanes available, although the set of images is much larger, we can combine the 2D and 3D information together. Effectively, we are adding a 3D term in the discriminator. But if you look at the behavior that the gain we make, so the Platonic GAN is only using our method. The 3D GAN is a GAN setup that works directly in the voxel setting. The Platonic 3D is a combination of 2D and 3D. And you can see that the improvement going from Platonic GAN to only a 10% 3D data is quite marginal. And we are getting close to ground truth even without having access to 3D data. So as a stress test, we went and collected some extreme cases where we have these mushroom examples. You see these mushrooms. The method assumed that the mushrooms have been segmented out, and these are the reconstructions from the single view for each of these images of these classes. So this is showing the reconstruction of one of the mushrooms. And here's an example with the volumetric rendering, which is absorption with the X-ray vision, where we have a transmission model also associated with it. So this started our journey to see how much of the 3D world can we infer from only image observations, but unlabeled image data. And that brings us to the next topic in this direction, where we are saying, okay, we can now have generations of 3D objects from image examples and unannotated or unlabeled image examples. Can we go beyond a single object to scenes? Also in last year's ECCV, this paper, which I would imagine several of you are familiar with, the HoloGAN paper was presented, which had quite a similar pipeline, I would argue. So if you see here, these are the images of the rotating of the cars from single observations. The fundamental difference from what we had for Platonic GAN was, instead of doing a volumetric occupancy model, Tu had this really clever idea of doing a volumetric model, but at each cells, instead of just occupancy, a deep feature is learned. The 3D transform, which is moving the camera, and the projection unit, as I explained, are exactly same. However, the projection being handling deep features, the camera array handling is same, but then the final image formation is through a ADA-in block, which are shown in the green highlighted ones. Right? So what it learns is both the deep features and the voxels, along with how to render it. However, that work cannot handle object level manipulation. So for example, I want to move the car from left to right or rotate it while keep the background fixed. That's my target, which is not what it allows. And this is not quite satisfactory, because if we think of what we have been doing in graphics over many decades, is we have now a solid understanding of how the image formation works. So in this case, you have a set of objects that can be inside the view frustum or outside. We can move the objects around and we can get a 2D images. Now, these objects are often arranged in hierarchy in the form of a scene representation, or what we call a scene graph, where each object can be individually manipulated in terms of translated, rotated, scaled, etc. And we would like to have the same amount of control, even though the representations are going to be not quite explicit, but in a more abstract, deep feature style. So what we have proposed is an object level decomposition, again by structuring the network using the inductive bias, that we have knowledge about the image formation model and how we would like the controls. So let me explain the structure and then justify why this is a good way of structuring the network. So all we have, and the network is going to be trained only with image examples. So what we have here is a background model that is going to be learned, that's on here. And then we have each row denoting each individual object. So we have a collection of k objects in this case. And then we have a scene composer function, the one in the blue with, as you see here. I will talk about what the scene composer is supposed to do. And then it creates a voxel of deep features, which is in the scene coordinates, which we observe from a camera. And now we can do a known camera transformation to reposition the deep features in the camera coordinates. And then we have a camera projection unit that essentially traces a ray along the camera path to collect the deep features from the structure. And then we have the encoding of this in the image domain to form the final images. Now, there are several things to highlight here. First of all, the features are associated at the voxel level, but at each voxel, we are learning a deep feature associated to that point. Now, the number of such individual voxel collections we have is equal to 1 for the background and k different voxel collections, 1 for each object. This is a fixed number of objects for now. Okay. Now, the scene composition, what it does is takes these individual objects, very much like a scene graph, and puts them together per voxel. And the voxels are in correspondence at this stage. And the way we do the scene composition, we tried various options, including max pooling, average pooling, mean pooling, and other options. But in the end, we found that the max pooling across the features per voxel gave the best and the most reliable results. In terms of the individual object control, essentially what we do is, according to the known transformation, whether it's scaling, rotation, or translation, we sort of teleport the features to the corresponding locations in 3D voxel space as determined by the individual transformations. Now, if you want to compare this with the hologram architecture, you can see what happened is the right part is remaining same after the projection part, but the main change has been the structuring of the network at the individual background and the foreground object level, and the learned scene composition function as we see here. This gives us explicit object level handle to the controls. So here's a sequence showing what is going on. So at training time, we are randomly changing the appearance and the location of objects to train this one. And then at inference time, we can change the background. We can move individual objects around. We can also add new objects, one object or multiple objects, and get these final output, right? So let's see one more time. So this is a training time where we are varying all these input ones. At inference time, we can change the appearance of object or background, or move the object, rotate the object, scale the objects, and add objects. Right? Note that at training time, although we are randomly sampling from appearance variation, object location variation, and object size variation, the corresponding parameters are not available to the algorithm. The algorithm only sees a collection of these images as a data set, and hence we can learn directly from the data set without requiring the corresponding annotations. Now, in contrast to supervised learning, we would have to assume that we have access to all the corresponding attributes at the time of training, but in this case, all we are requiring is access to the final images. Okay. So let's see how this performs on synthetic data. So this is synthetic data, means the data was generated synthetically, but the algorithm had access only to the images. So these are objects with specular highlights, as you will see here. So on the left are 2 cars, and we are rotating the cars while keeping their appearance and also the background appearance fixed. And you can see they are rotating nicely about their respective axes as indicated in our control. Here's the same thing, but now instead of doing a rotation, we are doing a translation. Note that the way we have specified the rotation or translations, they have been authored in a way that the objects are remaining separate from each other. Here's a similar test, but on a chair data set. This is a rotating set of chairs and couches. Note that the representation is not explicit. What the algorithm has learned, or what BlockGAN has learned, is a volume or a voxel collection where each location we have a deep feature that we have learned, right? So under rotation, it is possible that the object changes, and you can see at the back of the chair, because it never had the complete supervision, it needs to learn features along with the renderer so that the final image is correct. So when we interpolate with rotation, things can change, and you can see these changes. What I want to emphasize or highlight or bring to your attention is notice the fidelity of the shadows on the ground. So although there is no explicit light model, it still have learned how the shape of the chair leads to different types of shadows on the ground. So on the right is a similar example, but now we are translating this back and forth in the scene. Okay. Because we are learning on unlabeled images, we can use the same thing directly on real images, and this shows the power of the method. So on the top left, you can see a set of cars. Each of them, we are rotating the car individually. And note that unlike BlockGAN, now the background image, or the background, is not changing because we are changing only the object or a single car at a time. Here we do the same thing, but now we are moving the car left to right. Note that the background completion, or the in-painting like thing, when the new parts get unoccluded, that's naturally fits with the background. Bottom left, what we're doing is now we are doing anisotropic changes. We are scaling the car up and down, and notice the reflections on the windscreen and other things adjust accordingly. And the background largely remains unchanged or changes as it should be. And here, what we're doing is we are showing an interpolation result where we are changing only the appearance of the car. So the background should not change, as you can see here. Qualitatively, what we are trying to show, that the fidelity of the results according to KID scores here is quite close to GANs trained explicitly for image reconstruction. However, our strength is not in just the plausibility of the output, but we have object level control, which is not present by the other methods, especially by HoloGAN, because it had only scene level control, not individual object level control. So by object level control, to reiterate, we have rotations, we have translations, we can interpolate the background, we can interpolate the foreground, we can stretch the objects individually, we can combine, or we can almost do vector arithmetic, but in the deep feature space of combining appearance from one object to another, and we can also add objects in this thing. So I think it fits quite nicely to the theme of this workshop, where these deep features are modeling both the geometry along with the appearance of these objects. Now, in the last part of the talk, I will talk about what can we do beyond images if we also want to go to videos. Let me start again with the BlockGAN, where we assume that the object states are independent. Now, this assumption is easily broken if the objects are not independent. For example, if you have a stack of objects that are sitting on top of each other, of course, the positions and the orientation of the objects depends on the other ones below it. So if we run BlockGAN on such a data set, what it learns, it doesn't learn that the objects are separate, but from the generated image on the left, it puts everything on the background. So we do not get any object level control. We can either get a different set of blocks or not, but we cannot move or add new blocks at a time. And to address this, we make another change to the BlockGAN architecture, where we introduce this new module, And this is although the diagram you see on the top is different from what you have on the BlockGAN on the bottom, the main change is this module, the capital gamma, which we call the interaction module. So what it's trying to do is explicitly model the interaction between the objects, and as a result, the states or the theta i's, how they get affected. So what we are doing essentially is we are individually modeling the objects as before in BlockGAN, getting this theta I hat, and then we feed all of these to the gamma unit along with the appearance vector, or the sort of object vector. Note that the ZIs capture both the appearance and the geometry of the object. And this interaction module gives new states or new theta i's that tells us how the object should adjust, both in terms of geometry and their appearance, that can then be rendered out as before. Now, there are certain aspects why these things are coupled. For example, if two objects are shiny and come close to each other, due to their interaction, we would expect their appearance to also vary, because we would start to see their reflections onto each other. So their appearance vector should also adjust. Now here, theta i's denote the explicit position, but we'd also like to model the ZIs. Okay. So how do we capture this module? We have a very simple way of characterizing this interaction. We use an MLP given by the gamma that captures the interaction between any ZI along with all the other ZIs, right? And this is done in two parts. So we have this individual gamma one that captures this, but it relies on the state of the current object with all the other objects. And this is captured by the G function. The G function captures the pairwise interaction between the objects. And the way we learn this is, again, using another MLP, but it's a shared set of MLP, which is given by the G function. So essentially, we're learning the F function and G functions, and the composition of these gives the gamma function. And then when we stack it together, we get all the K interactions. Okay, so this is how we model individual scenes, or a scene with a collection of objects. But there are sequences, like I explained with the stack of blocks, where we have an ordered sequence, which means we can have a Markovian model where each object only depends on the previous objects, but not on the first. So the first object, the theta 1, can be modeled by itself, but then all the subsequent objects, so theta 2 will depend on only the theta 1, and theta 3 will depend on theta 2, etc. Okay. So this allows us now to get the stack of blocks, as we have explained, and when we decouple them, then they are indeed not all stacked to the background, but we have object level control here. And the object number shows how they appear. So 2 depends on 1, but not the other way. 3 depends on 2, 4 depends on 3, etc. Note also the realistic shadows we get on the ground. If we go beyond this ordered set to dynamics, then we would have a dependence in the temporal aspect. So we can extend the same idea along temporal aspect. And the way we model temporal aspect, we are modeling the velocity at any time. And then we can add the velocity to the current state theta to get the theta for the next state, or t plus 1. So the velocity one is again moduled by a stack of MLPs, very similar to how we did the ordered, but instead of a spatial ordering, now we have a temporal ordering. So we have an F function capturing the interactions, and the H function is a stack through the G's, which capture the interaction between the objects, right? So for example, if two cars are coming together, then once they come together to avoid a collision, they would be steered away. So here's an example of an unsupervised setup where all the algorithm sees is a top view of two balls, the orange and the blue balls that we see from the top view. And it's an elliptical view, elliptical ball. So as the ball is moving around, you can see that it traces out not a linear path, but it's on a bowl. So it sort of curls along the profile of the ball, and it very nicely follows the ground truth path, as you can see given here. So as we go from left to right at this time, this is a sequence where we show it on cars. I will show you some videos afterwards. And here's another sequence where it's a car as it moves from left to right. The car, we see more instances of this. So if you see the cars carefully, the one in green, is turning to the next lane, and you can see that the path is following. It's not a linear path, but it's bending around the corner, which is a really nice aspect. Note that here, just to appreciate the complexity of the task, the network was only given a stack of images. It was not told what cars looks like or whether car is the relevant objects here. It says model as object anything that moves, and it's not only learning how that object looks and appears, but it also modeling how they move forward, or the state move forwards in time. So it's learning not necessarily the geometry and appearance in a decoupled way, but in a coupled way, it's learning by the deep features, and then also how the features are transferred in this voxel grid over time. Okay. So we can again do the object level manipulations like we have shown in BlockGAN, but now it's a more improved version because it allows objects to be correlated, like in a stack of objects or cars moving next to each other or in tight configurations without bumping into each other and keeping their identity separate. When we compare with other methods in terms of FID score, ours is clearly better, as you would see here. So lower is better here. And the BlockGAN 2D is the version that we have used here. And you can see even on the Clever dataset, the shape stack that we showed are the real traffic cars. Ours is significantly better. Okay. So here's the shape stacks. The top are the input images, and the bottom are the generated ones. And here's on a real traffic sequence. So these are the real images. These are not our generated ones. But here are the generation results. Right now, some of the cars are moving straight, and that doesn't look quite as impressive. But the ones that are my favorite are the one that turns the corner. Now, even when the car is moving straight, note that because of the angle of the camera, because it's not orthographic, the size of the car has to change or get bigger as it comes closer to the camera. Also notice the quality of the shadow on the ground. And this will be something I would argue would be quite difficult even in the supervised setting to get to this realism of interaction of the cars and the fidelity of the shadows. The images are indeed quite blurry and still very small, and I'll talk about that a bit. So in summary, what we presented was deep learning deep features directly from unlabeled data in the form of single images or also video sequences. Resolution remains a bottleneck, and that's because these methods, these unsupervised methods, so far it still requires a lot of training time and also a lot of data. So we cannot yet go in higher resolutions, but we believe a multi-resolution approach would be the next step to try here. What I have shown so far are mainly unconditional generation. So we do not have an encoder that I can project images to this space, or I can project sequences to this space. So that's a very natural extension that we are looking at. That can we do conditional generation and explicit then handles on? Can we project a particular car image and a particular chair image into the BlockGAN space or the relate space and then interact with them? And what we haven't done yet, and that's the next big goal to pursue, is can we now do edits, which does not mean editing the coordinates, but editing the materials, or editing the actual substances of the objects. And that relates to the question that, is this the way to go, the learning from the unlabeled data, or we also want some hybrid approach where we have explicit overfitted models like you would have with the NERF or NERF in the wild setting, where we overfit to a particular object and scene. Then how can we sort of combine objects or these instances or the deep assets learned from unlabeled data and combine it with those explicitly learned from annotated data where we have annotation where we have multiple observations of the same scene. So with that, I'd like to conclude my talk. You can find our code, data, and papers on our website. Please reach out if something does not run or the data set is not fully available. We'll try to sort it out very quickly. This is really an exciting space with a lot that needs to be done and a lot that can be done. And I look forward to the other talks in this session to see where this area of learning the geometry and appearance together is going.
Thank you so much, Niloy. This was very inspiring. Can you hear me okay?
Yeah.
Oh, okay, great. Yes, I wasn't sure. This was really an inspiring talk. We have some questions from the audience. I'll read them to you. And so the first one is from Alexander Safin, and he asks, what tricks have you used to prevent the artifacts and similar problems from the GAN? Do the artifacts from 2D rendered images back propagate to the 3D model?
Thanks, Alexander, for the question. First of all, this was a unique experience for me listening to my own talk because I wasn't sure about the network. I believe your question is more regarding the Platonic GAN, the first one, Plato's escaping Plato's escape. So yes, this is a challenge that we have to backpropagate through the 3D models, and because we have an explicit occupancy representation in that work, so this is we found that it's important to have a good distribution of the view sampling, and it has to match the view sampling of what is observed. So let me give a particular instance. For example, when we are working on a car image data set, right, and we expect that the car is viewed from all possible directions, or distribution of the top hemisphere. Now, if in the test data set, or no, sorry, the training data set, the cars are all from showroom car images, they're often taken from a narrow view angles, from the front, just left and right. So there's a mismatch in the view distribution, and that means that the training will collapse. So in that sense, the next level of difficulty will be also to learn the view together, the view distribution with it, but we found it too difficult to do in a completely unsupervised way. We have to get a good view distribution that matches the training data. Yeah.
Thank you, Niloy. Another question from Thomas Singer. Thanks for the talk. Are you aware of any works that extend Hologan to reconstruct 3D mesh for a single object? If the final task is to output a mesh, is it a good idea to learn using implicit representation and then use marching cubes to get a mesh?
Yeah, thanks, Thomas, for the question. Really an interesting question, and this is something we have thought about, we are thinking about, and I do not know what the right answer is. Let me say what some thoughts about this. So first is, it's not even clear if we need to output a mesh. So in the BlockGAN work and in the relate work, we have features on a voxel representations. We can also have features on an implicit representation, right? Because it doesn't have to be explicit. And unless it's a requirement where we need the mesh for maybe fabricating a model, maybe we should forget our traditional graphics courses where we always assume that a mesh needs to be the final output. If the final output is an image or a video, it's better for the representation to be able to optimize both the representation and the rendering function at the same time. And that's something also came up when Angela was giving the talk. This is a direction I expect more a combination of these two rather than looking for an explicit meshing.
Thank you, Niloy. Yeah, I think these are interesting times for 3D people asking themselves, is 3D the holy grail, or is just means to improve 2D? Yeah. I also have a question. So I noticed that in the BlockGAN, and also in the follow-up you showed with the videos, you're using multiple objects, but they have to be of the same class. But that looking at the architecture, that doesn't seem to be a real limitation. Is that a limitation, or am I not seeing something?
Yeah, you are correct. And we did some tests, but we did not have enough cycles before the submission to do it. So let me explain what the test we did. So there are two functions that are simultaneously being trained. One is the representation of the model, one is a rendering function. The rendering function can be shared as long as it has been trained in the same way. So if you're training for multiple classes at the same time, we want the rendering function to be shared. So if you're doing, say, cars and chairs and whatnot, it would be the same rendering function that is shared. If we do that, then it will be possible. And we did experiments later on, and this is indeed the case. But then the training time becomes even longer because we have to do over big data sets at the same time, times the number of classes. But I think it's theoretically possible, but I would expect more breakthroughs in this direction. So.
I see. Thank you so much. I think, yeah, there are a few more questions in the Q&A, but I think since the talk was slightly longer than others, maybe we'll move forward to the other talks. And if you are around, maybe you can take a stab at those offline using the Q&A. Yeah. I think you're
I'll do that.
Should be able to do that. So thank you again, and I'll pass the mic to Srinath to introduce our next speaker. Thank you, Niloy, and we'll be seeing Niloy in the panel as well.
Thanks, Niloy and Or. That was a great talk, and looking forward to seeing more discussion in the panel. Just as a reminder, we are running about 15 minutes behind schedule. So please move the schedule about 15 minutes in case you're referring to the schedule online on the website. All right, so with that, it's my great pleasure to introduce our next invited speaker, Noah Snavely. Noah is an associate professor of computer science at Cornell University and Cornell Tech, and also a researcher at Google Research. Noah's research interests are in computer vision and graphics, in particular 3D understanding and depiction of scenes from images. Noah is the recipient of the Presidential Early Career Award for Scientists and Engineers, a Microsoft New Faculty Fellowship, a Sloan Fellowship, and a SIGGRAPH Significant New Researcher Award. And today he'll be talking about reconstructing the plenoptic function. And Noah, I'll give you a 20-minute warning. And apart from that, the floor is all yours.
That is so cool. Thank you. So let's see. I think I'm supposed to share my screen.
Yeah,
so
do you have? Yeah.
Oh, has anyone ever clicked on the button called Optimize Screen Sharing for Video Clip? Is that a button I should click on?
If you have videos and audio, I would encourage you.
I've never seen that button in my whole life, so I'm a little scared, but I'm going to try it. Thank you.
Okay.
All right. So do you think you can see my screen?
Yes, we can see your screen.
Okay. Let me try and. Do you think you can still see my screen?
Yes, it's perfect.
Okay, this is great. So yeah, I'm Noah. Great to see you. It's a delight to be here. Hope you all are doing good wherever you are in this world. And yeah, so I'm going to talk about reconstructing the plenoptic function. And the reason is that a big motivation for, one of the big goals of computer graphics and other areas like art and photography, but especially computer graphics, is to devise ways to capture and experience the world in ever more realistic and compelling and vivid ways. And so, throughout history, people have done this with whatever medium was available, whether it's painting, like this painting of the Pantheon by Canaletto in the 18th century, or photography or stereophotography. So you get a vivid stereoscopic view of what a place is like. A lot of this in the interest of showing someone what it's really like to be somewhere. And it's not lost to me that this is has renewed relevance in this age of pandemic where it's hard to travel. And I could name a million projects and technologies that do this, VR, et cetera. But some projects that I especially love are ones that don't just try to capture like famous landmarks, but try to capture the whole world. So in this vein, one of my favorite ideas, which I think is maybe not that well known, is the Aspen Movie Map project from the late 70s and early 80s, where this was basically radical proto street view 30 years ahead of its time, where they installed a film camera on top of a car, the group from MIT led by Andrew Lippman, and drove it through all the streets of Aspen, recording to optical video disc, and to where you could then take that data and install it in this, futuristic looking interactive experience where you could then, virtually drive through Aspen and turn to whatever street you wanted, and it would do, through the magic of optical video disc, randomly access the right frames. And you can have this like rich experience of what it's like to be in Aspen. And there's this great video online of from the time of someone using this experience, and some parts of this have aged better than others. But it's this really amazingly pioneering project on capturing the whole, capturing a whole city, and not just spatially, but also temporally. So they did this. They drove through in summer and winter, and you could interactively switch between them. The idea being like a place looks very different at different times of year. So by the way, if you ever wondered what a SIGGRAPH 1980 paper looks like or could look like, here's what it is: like this beautiful typewriter manuscript. And so what a lot of this work tries to get at in some level, oh, by the way, I have some, you might see a cameo from kids in the background, is this philosophical idea of the planoptic function, which was idea introduced by, or conceptualized by Adelson and Bergen in their seminal 1991 paper. But the planoptic function is this hypothetical function representing all light rays that could ever pass through space, representing everything we could ever see. And by the way, these good slides are stolen from Alyosha. And you can parameterize this function of all light by 7 parameters. So the planoptic function P is a function of XYZ position, like where your eye is, theta and phi, which direction you're receiving light from, the wavelength theta, lambda, and time t. Okay, so just recording of everything you could ever see at every moment from every position. And as a corollary, it contains every photograph and every movie and everything that anyone has ever seen and everything everyone hasn't seen, like the tree falling in the forest. Just a complete description of the visual reality. And of course, it's completely hopeless to capture or store or represent this, but we can still try. And so doing so, an effective way to capture and experience this planoptic function would be like a holy grail in computer graphics. You could teleport anywhere at any time. Okay, so how could we actually do this with modern tools? So, in the last 5-10 years, we've gotten pretty good at capturing light fields, like little balls of the planoptic functions sampled at a particular position. So, we had, this is particularly relevant for VR applications. So JUMP was introduced by Google 5 years ago. Ring of GoPros capturing stereoscopic panoramic video. At this year's SIGGRAPH, there's another Google camera, from Paul Debevic's group, hemispherical capture rig, and you can get amazing like local slices of the planoptic function captured with this camera. Very rich experience of a slice of space and time, a relatively small slice of space and time, but with compelling parallax. Okay, so how could we scale this up to all of time and space if we want to capture the whole planoptic function? Well, you could put light field cameras everywhere and just leave them running at all times capturing data, but then we'd be in like surveillance state, and you couldn't even practically do this. You can't like densely fill space with cameras, or there'd be no space left for anything else. So instead, you have to somehow sample the planoptic function and reconstruct it from those samples. Okay, and so how could you do that? Well, a modern version of the Aspen Movie Map project, of course, is Street View, where you have a mobile camera, panoramic camera in this case, driving through streets, and dramatically larger scale than the Aspen Movie Map project. So Google Street View drives almost everywhere, capturing data all the time. Massive geographic coverage. So that's like maybe the closest we've gotten so far to capturing this planoptic function, but it's still very sparse in space and time. So these panoramas are 5 meters apart. Might drive through a street in some city at a certain point and then drive close to there again, maybe the other side of the road 6 months later. So still very sparse sampling of this function. Another idea you might have, is like, let's use all the photos on the internet as our planoptic camera. And you can do the kind of typical thing, search for photos of the Trevi Fountain on Flickr, reconstruct them. And what you'll see is you'll get these like, here's a point cloud reconstruction of the Trevi Fountain with all the camera positions shown. So you'll get these spatially dense clusters of photos, but they're still spatiotemporally sparse. Like how many photos are taken at July 1st, 2010 at 4 p.m.? Well, probably 0. So it's very hard to capture dense spatiotemporal samplings, even whether it's photos on the internet or Street View or whatnot. So in both cases, we have a sparse sampling of images, images I at various times and places X, Y, Z, T, 3D positions and times. And so the question then is, how do we reconstruct the planoptic function as best we can from these samples? Chiming in for my daughter here. The goal is we want to be able to reconstruct or interpolate any new image from any desired position in time. And so, I feel like we finally are starting to have good tools like data algorithms, et cetera, for this reconstruction problem. So in this talk, I'll talk about 2 different efforts to reconstruct the panoptic function, one at landmark and one at city scale. And by the way, when I talk about the panoptic function, I'm actually not interested in, for the purposes of this talk, in dynamic objects like people and cars. This is not a surveillance camera. So you can think of it instead as you want to render a long exposure photograph where all the moving objects are blurred away and you're just seeing the static scene geometry. Okay, so first I want to talk about a project that appeared here at ECCV with Cornell Tech PhD students Zhengqi Li and Wenqi Xian, and new Cornell University faculty member Abe Davis, called crowd sampling the panoptic function. And I wouldn't normally show just play a video like you're watching TV, but Abe did such a good job at creating a video for this project that it seems criminal not to at least show part of it. So I'll turn it over to Abe to sort of motivate this project. By the way, one of the innovations I really like is an animated author introduction.
Crowd sampling the planoptic function by Zhengqi Li, Wenqi Xian, Abe Davis, and Noah Snavely. Most of us carry a camera almost everywhere we go. Nowhere is this more apparent than at a popular tourist attraction, where you'll often find as many cameras as there are people. And this leads to a lot of photos, which we can think of collectively as the result of a kind of crowd sampling over time. Now, a lot of those photos eventually get posted online, where they become freely accessible to anyone with an internet connection. So in this work, we explore how to use that crowd sampled data to turn regular photos into something that lets us move around a scene, both in space and across changes to appearance that happen over time.
Okay, that's like Abe setting a new bar for video production.
Crowd sampling.
In a CVPR talk. So let's think about this panoptic function. So let's imagine it, just for simplicity, in 2D. So imagine you have a 2D coordinates, one direction for viewpoint and one axis for time. And the planoptic function is a dense filling of the space, an image from each of the 2D coordinates in this space. Sorry, you need to go away. I'm in the middle of the talk, okay? Okay. It's like a real pandemic style talk. Okay, Charlotte, please go out. I'll be done in a few minutes. Okay, so now you can imagine different kinds of samplings of this panoptic function. So you can imagine a fixed time and excuse me, I probably have to move to a different area. A fixed sampling of viewpoint, for a static time, a sampling of viewpoints. So this corresponds to sort of standard view interpolation from a fixed time. And we have good technologies for doing that. So you can also imagine, okay, what does a row of this matrix look like? So a row of this matrix corresponds to a single position with varying time. And so, that's basically a time-lapse video. So you can imagine, turning an image into a time-lapse video by, techniques like style transfer. Okay, but in our case with this crowd sample data, we have a more or less random sampling of this panoptic function. So we have images captured at random points in space and time. And we want to be able to reconstruct, fill the space densely, reconstruct the panoptic function from these scattered views. And even worse, like the timestamps we have for these images are not super accurate. So many times they're complete garbage. So we don't know exactly where many of these photos are registered in this kind of 2D planoptic space. So I'll hand it over to Abe again to show, one of the big contributions of this work is a new representation where you can, take all this data and learn how to both change appearance and change viewpoint jointly.
So to address these challenges, we introduce a new neural scene representation called deep multiplane images, or deep MPIs, which offer a way to represent viewpoint slices of the planoptic function that interpolate meaningfully between changes of appearance that happen over time.
And so you see, this is what we can render. We can render both varying views and varying appearance. And so I'll talk about this deep MPI in a second, but overall we also have a new method for computing a deep MPI from a set of images. So you take your images of Piazza Navona or whatever location, you optimize a deep MPI specifically for this location based on those measurements. And that allows you to render both varying appearance and varying view position. Okay, so how do we do this? Well, of course, you first start by running structure motion. We use ColMap to register lots of views of these landmarks. And we focus on views close to a reference position. So we take all views within a sphere, within a certain distance of some reference view. And then we build our scene representation, this deep MPIs, on multiplane images or MPIs, which have been very successful 3D representations for view synthesis in the last few years. So if you don't know what an MPI is, what it is a set of views, a planar set of layers. Oh, I think, interesting. Okay. Yeah, a planar set of layers. My mouse is being controlled by my daughter. I'll have to go get my trackball. Sorry, can I have my trackball, please? Thank you. Thank you. Okay. Thank you for bearing with me. It's always fun with kids. So MPI is a set of planar layers arranged in depth, centered on a reference view. And each of the layers has a RGBA image. The alpha channel represents transparency. And so if you move the camera, if you move the camera to the reference viewpoint, these images will coalesce into this compelling 3D description of the scene that allows for a varying viewpoint. In this case, this work from John Flynn also allows for a varying time. But mainly this MPI is useful for rendering, for view synthesis in a set of views around a reference view. Okay, so an MPI consists of, again, a set of layers. Each layer is an image, so you can think of these as having pixels that are like voxels. Each voxel is an RGB color and an alpha channel. This alpha channel sort of represents the geometry or visibility information for the scene. Okay, so to render with an MPI, you can warp these planar layers from the reference viewpoint to a desired target viewpoint, and then composite them using overcompositing, standard computer graphics overcompositing, to get the rendering of the view of that viewpoint. So MPIs are really good at representing realistic 3D effects as you move the camera. What they're not good at, because they don't encode this at all, is representing time-varying appearance. There's no way to vary the appearance of an MPI or to interpolate appearance across time between two kinds of appearances, like day and night. So instead, we augment this MPI representation with a learnable latent feature vector in addition to an RGB alpha channel component per voxel. And the idea is that this learnable latent feature vector is going to learn how to modulate the RGB color according to a desired appearance. The alpha channel, though, is going to be fixed. We're going to assume that scene geometry is fixed over time. And so you can share alpha across time. Okay, so how do we compute this deep MPI? Well, there's two stages. First, we optimize more or less a standard MPI, fit to all of the input views. And then we take the alpha and color channels, optimized in that first stage, and learn these latent features as well as a neural renderer that will capture varying appearance over time. Okay, so I just wanted to briefly talk about these steps because I really like some of these visualizations. So to optimize this kind of standard MPI, we first take all of the input views, all of these internet photos, and project them to a plane sweep volume and average them at each plane sweep slice. So this is a visualization of a plane sweep volume where we've averaged all of the different images onto different depth layers. And the reason I really like this visualization is it's like you took a very strange camera with a very weird aperture and focused it at different distances in the scene. This is what you get. It's like a very narrow, strange field, depth of field image, focusing it, sweeping from back to front. And also you've averaged the appearance. So it's kind of what the average illuminated Trevi fountain looks like. Okay, so when, from this plane sweep volume, you then optimize, you initialize the color values of your MPI with that plane sweep volume, and then you optimize the color and alpha layers by rendering the MPI to each of these input photos and minimizing reconstruction loss using gradient descent. And very surprisingly, to my surprise, you get a decent average MPI, even though you're fitting using mean squared error to all the varying, very diverse appearances in the input set of images. So you kind of get an MPI, here I'm showing the MPI and rendering different viewpoints, that captures the average appearance of the scene. And if you render the alpha values as a depth map, you get something that actually, it does look like a depth map, not a perfect one, but reasonable. Okay, then once you have that initial standard MPI, you then upgrade it, augment it to a deep MPI with these learnable features. And so the way this works is that you learn those features jointly with a neural renderer, I'm calling it G here, which can map those deep features to standard RGBA colors, okay? And again, the alpha channel is just copied over. We reuse the alphas for all different time appearances. Okay. How does it know what kind of appearance to generate, like daytime, nighttime, et cetera? Well, there's going to be a latent vector, Z, that describes the appearance and modulates the renderer through an ADA-N, adaptive instance normalization layer. Okay, where does that Z come from? Well, the Z comes from an encoder. So you take an exemplar image that you want to match the appearance of. So generate a light field, but from this appearance. And you feed it into an encoder and learn to encode these latent Z vectors. And by the way, there's some details here, like it's better to not feed in the exemplar image directly, but to first reproject it into the reference view via the MPI so that the encoder sees images that are all registered more or less to the same viewpoint. So it doesn't have to learn the, this part over here is in shadow, but it's actually in this part of the image because of the camera viewpoint. This registration takes care of that. Okay, so now we know how to render. And so once you produce a RGBA MPI, you can render it to the target, to this ground truth image viewpoint, compare it to the actual ground truth image. That gives you a loss function that you can minimize to learn all of these different learnable components. The renderer, the encoder, and the deep MPI features themselves. And again, this is learned per scene. Okay, so we also create a big data set, lots of, bunch of different scenes with lots of foes for each scene for these kinds of reconstruction problems. And here are some results. So here's the Trevi fountain rendered with 6 different appearances. And so we basically rendered 6 different light fields at different times that allow for varying view and appearance. Here's the same, but for the Pantheon. From day to night. Here's the same, but for the Piazza Navona. Of course, Rome is full of great places to take photos. And so there's been recent work on this problem, most notably neural rendering in the wild, which, the one big difference with what we're doing is a lot of these previous works are kind of style transfer or, neural rendering and image space based, where you don't guarantee consistency across views. So if you look at these two baselines, you'll notice they flicker more than our method because they don't have a global scene description like our MPI. You also, it captures the scene appearance somewhat more faithfully as well. You can also interpolate appearances. Here's 2 images. Here's an interpolation between them. One thing that it turns out is very difficult to capture is cast shadows. And we don't perfectly capture them, but we're doing a better job than the baselines in capturing kind of the movement of shadows as the sun moves through the sky. And we can also render what we call 4D photos, which is photos with varying view and simultaneously varying time of day. So from day to night, and the lights of New York City turn on at the right time, and so on. Okay.
Oh, sorry to interrupt, Noah. Just your 22-minute reminder.
22-minute reminder.
So you have 3 minutes.
Yeah. Okay. So okay, 3 minutes. There's been very recently we've seen work that NerfW from Google that does a also tackles a similar problem, but using Nerf as the underlying scene representation as opposed to MPIs, which gives you a much greater capability to move the camera larger distances, but it's much more expensive to learn and render from. But just in general, I've been working on these internet photos for a long time. And I'm just amazed at sort of the progress since when I worked on phototourism, my PhD, of how far we've come in this neural rendering in rendering the world from internet images. So 15 more years of work with all these modern tools is giving great results. So you can see more at this webpage. Okay, so I have a few minutes to talk about just another project that's very dear to my heart with collaborators Andrew Liu at Google and other great collaborators, Shiri Guinnessar, Tinghui Zhou, and Alyosha Efros. And so, again, we don't want to just reconstruct landmarks. We want to reconstruct whole cities. Like, I want to know what the Upper West Side looks like at this point, right now, or what this point in the Upper East Side of New York looks like, 10 years ago. And there is a tool for doing this called Google Street View Time Machine, where you can go to Google Street View and dial back to historical views of, what this point looked like at different times, near the Flatiron Building. So this is great. You can take any point in the city and dial up a number of views of it, but these are still very sparsely registered in time. So maybe 1 to 10 views over the course of 5 to 10 years is available in Google Street in Time Machine. And also, these views are imperfectly aligned. So if you take a set of nearby views and view it as a time-lapse video, it's not perfectly registered. So what you can say is maybe Google Street View is full of wonky time-lapse videos that are very strangely sampled and very short and also imperfectly aligned. But these time-lapse videos are a very rich source of training data for learning how to reconstruct the panoptic function. So you can think of a single run of Street View, again, if I look at this matrix of view and time, as like a sparsely sampled column of the panoptic function. And if I repeat that Street View run by the same street over time, I'll get different samplings of those views, again, not quite exactly registered in space. And somehow from this, I want to reconstruct a full panoptic function. So it's sort of a matrix completion task. So we pose this as a factorization problem, just noting that for the same scene over time, there's things that stay the same, like the buildings and their geometry, and things that vary, like the sun position and the sky appearance. And we want to be able to factor these permanent and temporally varying factors. And if you can do that, now you can fill in these missing entries of the panoptic function by keeping the permanent factors fixed and changing the temporally varying factors, like the sun position or the sky conditions, etc. So how do we do this? Well, just very briefly, like if you think about this problem, it's very difficult. If you like take a single image and look at a patch, some of the pixels are due to permanent factors like the building appearance. Some are due to time varying factors like the shadow cast on it. They're all entangled together. From a single image, it's very difficult to get a training signal for decoupling those. But we don't have a single image. We have these wonky time-lapse videos across time. And this provides a much richer signal for learning this disentanglement. And we don't have a single stack. We have millions of stacks across New York City and across the world. Millions of these wonky time-lapse videos that I'm calling stacks. And so we sample these from all over New York City. And the basic idea is we learn a disentangled representation. So from a single stack, we factor it into a time varying factor and a permanent factor per image. Not to go into too many details, but we represent both in this time varying factor, the kind of ambient appearance of the sky and clouds with a general latent feature like in the previous project. And we also have an explicit representation of sun position. So this histogram is showing is like predicted sun azimuth angle for this, for each image in the stack. And all of this is learned without extra supervision, just from having access to these wonky time-lapse videos. We also learn a permanent factor, which kind of encodes, geometry and albedo, things that don't change across the stack. We then have a decoder that takes these latent factors and decodes to standard sort of intrinsic image decompositions, a shading image and a reflectance image. These shading images we get, though, I just want to mention, are very beautiful. Like, to my eye, these are much better than standard intrinsic image results. It's like this whole scene is covered in snow. The buildings are actually devoid of almost all reflectance. Okay, and then you can reconstruct the original stack using that decomposition, and then that gives you a signal to learn from. the main training signal being the fact that the reflectance is shared, like that doesn't vary over time, and that you want to reconstruct the original data. So you can then apply it to new images and new cities. There's an alignment problem I'm not going to detail in, but we also jointly align these stacks because they're not perfectly aligned. This alignment is learned in parallel with learning reflectance and shading. So this is just a time lapse of this kind of iterative learning process. Once you can do that, you can modify, once we learn this, you can modify illumination factors, like swap them between two images, decode the new shading images, and then by virtue of that, learn to relight images by transferring illumination from completely different images of completely different scenes. So now we've taken this originally cloudy image of this scene, and now the sun is as if it was in this original image. Okay, I think I'm running low on time, so I'm just going to wrap up very quickly here and say, you know, this allows us to generate these compelling time-lapse images that are sort of, you know, these rows of the panoptic function complete by synthesizing new times. So with that, I'll just summarize. We haven't achieved world-scale view synthesis yet, but we've taken baby steps towards that. Data is still king. These projects are, I'd say, mainly possible because we have access to data like Street View and millions of tourist photos. But a lot of challenges remain. Like, we still want to scale up to the whole world. The lighting materials we're learning are still physically realistic. Like, there's a lot of, you know, the shadows are not physically rendered from like occlusions of the sun, but are synthesized. We could do a lot better there. And more generally, many of the things that bring scenes to life are still missing. Like, these scenes are empty. There's no people moving around or cars driving by or clouds drifting by. There's no audio. These are things you would need to really make compelling experiences. And also long-term changes are not modeled. So we kind of are capturing the medium scale illumination changes, but not like the buildings growing over time because they're being constructed and the people milling about over a scale of a few seconds. So with that, I'd just like to thank all my collaborators again. And if you want more information, you can visit these sites. Thank you very much.
Thank you so much, Noah, for this very interesting presentation. I must say that we particularly enjoyed the cameo from your daughter, and you handle it really well. We must apologize for keeping you away from her.
Oh, it's just, yeah, thank you.
All right, so we have a time for maybe one quick question. I'll go to the QA box here. So Jipeng asks, how many images are needed to learn the disentangled representation per scene?
Okay, so I think this is probably talking, okay, I'm not sure if this is talking about which project. I'll talk about the, I just want to highlight one big difference between these two projects is for the Landmark project, it's optimized per scene, and we probably have 1,000 photos. For the Factorizing a City project, we learned this factorization over the entire city. So it's shared across all of space. So despite having, you know, just a few views of each particular location, we have millions of views across the whole city. And it's learned jointly on the basis of all those images.
Okay, maybe one more quick question. Alexander Safin asks, what type of scenes are the most difficult to recover in the crowdsourcing planoptic function paper?
Oh, that's a great question. So I think there is, so scenes with very strong cast shadows are hard. And maybe you wouldn't think of it, but scenes that are very, very crowded are hard. So in the Pantheon, you might notice some ghostly things appearing in the foreground. It turns out that because we're not modeling dynamic objects, if there are almost always people in a scene, those throw the model off a lot. So there's like, I think NeRFW has a way of handling this, but in general, that makes life hard and is another reason to try and capture dynamic aspects in some way.
All right, great. Thanks a lot, Noah. And there are a couple of more
everybody.
questions. So if you want to take it offline and respond to them via text, that would be much appreciated. All right,
Thank you.
Let's thank Noah again. And I'll pass the mic on to Or to introduce our next speaker.
Thanks again, Noah. This was very exciting and definitely a lesson in how to remain focused and manage interruptions during a presentation. So this is really, really great. So the next speaker, I don't think needs much introduction, but I'll do that anyway. Our next speaker is Professor Jitendra Malik. Jitendra, if you're around, can you show your video and make sure that your slides are on? And while you do that, I can read some of your bio. Oh, I see you texted that you need permission. Let me see. Okay, we can see you, but we cannot hear you yet.
Okay, now I think, can you see me and hear me?
We can see and hear you, and soon we'll be able to see your slides, I assume.
Yes, I will do that too.
Okay, so while you do that, let me tell you a little bit about Professor Jitendra Malik. Jitendra was born in India in 1960. He received his degree in electrical engineering from Indian Institute of Technology in 1980, and the PhD degree in computer science from Stanford University in 1985. In January 86, he joined the University of California at Berkeley, where he's currently the Arthur J. Cheek Professor at the Department of Electrical Engineering and Computer Science. He's also on the faculty of the Department of Bioengineering and the Cognitive Science and Vision Science groups. During 2002 and 2004, he served as the chair of Computer Science Division and as the department chair of the EECS during 2004 and 2006, as well as the 2016-2017. Since January 2018, he's also a research director and the site lead of Facebook AI research in Menlo Park. And I myself had the pleasure to have Jitendra as my manager last year. Jitendra, without further ado, the stage is yours. I will give you a quick reminder in the 20-minute time, so you know you have 5 minutes left. And just as a reminder, use the Q&A button. This is for our attendees. Use the Q&A button to ask questions, and I'll read them to Jitendra at the end of his talk. And he'll stay here for the expert panel that we have afterwards. Jitendra, the stage is yours.
Thank you, Or. Can everybody see my slide? It should say on learning 3D.
Yes.
Great. Okay, so thank you for the invitation, and I've enjoyed listening to the other speakers. And I'm going to start with a historical journey. And this is from 24 years ago. So this was about 24 years ago, because I think this is SIGGRAPH week. So this was presented at SIGGRAPH 96. And the number of photographs used for reconstruction is on the order of like 20 or 30. And as you can see, we have a 3D model of the Berkeley Central Campus, and you can judge for yourself the photorealism of the rendering. So the point is, this is an area which has been quite successful. Okay, and so what have we achieved in the last 24 years? I think that if some of you saw Noah Snavely's talk, that was a good indicator of where we are. I think his own work, going back, I would put it like in the middle of these 24 years, say 12 years ago, is Snavely, Seitz, and Zelinsky work on phototourism, which showed how from collections of internet photos, we could get amazing 3D reconstructions of monuments like the Colosseum in Rome and so on. And then I think if I have to turn to work today, the work that I'm most impressed by is the NERF tradition from Milton Hall et al. And again, the latest results showing all the reconstructions of the Trevi Fountain and so on are very impressive to me. But the bottom line is that I think we have cracked at least one version of this problem. Given lots and lots of views, we can do a reconstruction. But this is in the setup of lots and lots of views. Okay. Now, what's next left to be done? So in my view, here is a core central problem which humans can do very well and we have not fully solved. So this is the problem that I would call the one of 3D-fying any image. So you're given just a single image, and as humans, we perceive it in 3D. So we can think of all the objects here and we imagine how they are in 3D. And that perception is one which evolves over time to greater precision, in the sense that when I look at this room from far away, my guess of the shape of the chair is probably driven by my priors. It's sort of controlled hallucination in a sense. But as I come closer and closer to the chair, I've got a much, much more accurate reconstruction. It's of this specific chair. And I think we need both these characteristics. Rely on your prior knowledge of that category when you're far away, and rely on the accurate knowledge that comes from stereo or multiple views or what have you, as you come close to it, and it should happen smoothly and cleanly. Are we there yet? So my assertion is that we are not there yet. Okay, so that's my big claim. And now the question is, what is the field doing? Because we haven't solved this problem. And I think this is the central problem. What are we doing? Okay, what we are doing is we are writing lots of papers using ShapeNet. Okay, nothing wrong with ShapeNet. I think ShapeNet helped the field a lot. But at some point, we have to realize when we are using this as a crutch. And the advantage of ShapeNet is that this makes the problem on a supervised learning. So we have images, we have these models, we render them, we get images. So now it's xi yi pair. Supervised learning is what we have the best technology for, so we just throw that at the problem. But ShapeNet is not the real world. Okay, scraped CAD models from the internet are not real objects. So that's a clear engineering critique. A more scientific critique is that supervision with CAD models is not natural supervision. I would argue, and I will get into more, this is a debatable point, but I believe that supervision from multiple views is arguably the only natural form of supervision. So, therefore, I'm going to take you down the path of asking basic scientific questions. How do humans perceive 3D? How do human babies learn to perceive 3D? So first question is about adult capabilities. Second question is about the learning process, okay? And then we need to create computational models for these capabilities. So for the first question, here is like the standard psychology textbook for perception, Steve Palmer's book. It has actually a big table of all the various cues there are for three-dimensionality that humans can make use of. I'm going to go through this at a very big picture level. So there's a very strong family of cues which have to do with motion, either motion of the observer or motion of objects in the world. And this is a slide which is originally from Gibson, which shows how this pattern of optical flow carries signal for 3D shape. You've all studied this in your computer vision classes, so I'm not going to go too much into this. Second cue, which again in psychology was realized from roughly 1840 onwards, is binocular stereopsis. We have two eyes, so slightly different views in the two eyes, and that gives us a signal. The mathematics is very similar to that for motion. But here is an interesting aspect, what I call pictorial cues. So the psychologists use the term pictorial cues for the cues for three-dimensionality which exist even when we have a single image. So like a picture, when you go to see a painting in a museum and you perceive three-dimensionality, that's based on pictorial cues. And here's a classic paper from Koendrink, Van Doorn, and Kappers, which shows that humans perceive this not just, they perceive depth, but they can actually, in fact, perceive surface normals at every point on the shape. And they were able to access the internal representation of the surface normal by this trick of asking humans to put little ellipses corresponding to a circle painted on the surface. So what are the different pictorial cues? These are going to guide us when we want to solve the problem of 3D from a single image. Texture gradients. Okay, so the basic underlying assumption here is that there is some regularity in the scene. In the scene, these slabs are all the same size. These circular discs are all the same size and shape, but they look different because they are at a different distance or orientation with respect to the viewer. And Renaissance paintings exploit this spectacularly. Okay, do our current computer vision algorithms in the deep learning era exploit this fully? I'm not sure. And of course, this texture gradients can apply to a single object. So here you see this object and you can hopefully see like a groove at the top and then pinched in from the side. So it can operate at the level of a scene or a single object. Shading, this is another very classic cue. So if you look at the object on the left, you feel like if you moved your finger on those lines, they would, I think, poke you. You feel that they are like ridges. And then on the right, those look like they are grooves, or they feel like they are grooves. Actually, the two images are identical. One is just a 180-degree rotation. So it's just made upside down. And this has to do with humans making default assumptions about the sun being above and so on and so forth. And I should note again for historical accuracy that the person who realized the cue of shape from shading was Leonardo. So this drawing is taken from Leonardo's notebooks. And you see a light source A, and then these different points on the human's head. They have different surface normals with respect to the light source direction, and that accounts for the differences in shading. And Leonardo insisted that painters should be aware of this and get this right. Okay, now let's turn to computer vision. So really classic work here. This is Berthold Horn's PhD thesis in 1970. So we're talking about 50 years ago. And Horn addressed the following problem. Suppose we know the lighting and we know the reflectance, then can we estimate the shape given a single image? And that's this is a little bit of text from his 1970 tech report. And this is essentially an inverting the physics problem. It is the beginnings of this inverse graphics paradigm. And you can do this under certain conditions. And by the way, techniques like this were used for reconstructing the surface of the moon. And but here you needed, if you make no other assumptions about the statistical nature of the world, you can't solve the problem in its full generality. So the full generality is that you don't know the shape, you don't know the reflectance, you don't know the illumination, and you have to unpack all of them. You have to factor out all of these from a single image. And this is the serfs problem that John Barron and I tackled some years ago. And the difference, why were we able to do it, which Horn could not? The difference was that we brought in some statistics and probabilistic reasoning. So what we said was not all shapes are equally likely, not all reflectances are equally likely. So you can have probability distributions over them. So then we can set it up in that way, and you find the most likely shape, most likely lighting, most likely reflectance map, which can account for the data. So it's analysis by synthesis in a statistical framework. And this enables us to track this, to crack this problem. This is the sort of classic intrinsic images problem. But there are other cues here, the cast shadows. So if you look at the spheres in B, they appear to you in the same frontoparallel plane, but some are lower and some are higher. Whereas in A, they appear like they're further back versus nearby. And the math for this is fairly easy to understand. Anyway, these are all classic pictorial cues, shape from texture, shape from shading, shape from shadows, etc. And in computer vision in the pre-machine learning era, I would say, worked out mathematical frameworks for this with lots of assumptions, which were not always necessarily true in the real world. And these are generic techniques, right? So these techniques work independent of the category of object. There's a second class of cues, which are also pictorial cues in the sense they are available in a single image, which have to do with recognition and familiar shape. And I'll pick two classic examples from this. So one is Blanz-Wetter from SIGGRAPH 99, which is work which shows how 3D, how if we have models of 3D shape of faces, then from a single image, we can essentially get to the nearest point on that manifold. And he has work from Cashman and Fitzgibbon, which tries to recover shapes of dolphins just from images. So this is really familiar shape. And I would argue that so much of what we have been doing in the deep learning era is basically building on this theme, right? It's the theme that you're reconstructing chairs from lots of examples of chairs where we are assuming that you have 3D. So that's the part which is to me a little bit of cheating, but it's perfectly reasonable to use lots of examples to build an implicit 3D model. Now I should note again for historical accuracy where this idea comes from. The idea of these deformable templates actually goes back to Darcy Thompson. And he did this in the context of biology and anthropology and sort of study of fossil heads, skulls, and so on and so forth. Okay, I'll spend a few minutes on this paper we wrote. This is like nearly 10 years ago. Chetan was a student of mine together with Antonio. We wrote a paper where we were trying to understand the visual perception aspect of how we see 3D in a single image. And the question we were interested in, this is a psychology paper, okay? The question we were interested in is, we know that we can get shape from shading, right? And we have models for that from Horn onwards. We know we can get shape from recognition of objects. So once you know it's a chair or a human head, that gives you a perception of a guess of its shape. Do both of these cues operate, or can we manage with just one? And so we did these manipulations where you could do blurring, which would affect the shading cue, but not the recognition-based cue. And we did it in a couple of different ways, and the details don't matter. But the bottom line was that hurting the shading cue actually hurts your perception of shape, and shapes become flatter. And humans are not consciously aware of this, but this happens in the results that we managed to elicit from their internal representation of the shape. And it turns out that recognition matters. If you can't recognize an object, you do not get its correct shape. So the bottom line was that this was a support for both traditions of classical computer vision. The generic shape from X tradition, which is shading, texture, etc., as well as the recognition-based tradition. And I think we should keep this in mind, because I think currently we are much more faced on much more biased towards the recognition-based tradition, because that's what learning makes convenient. So since we started to talk about learning, I want to make a few remarks there. For a few years now, those of you who heard me in various workshops have seen me emphasize this paradigm of research that I call Turing's baby. And this is essentially based on section 6 of Turing's 1950 paper. And he says, instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? So if this were then subjected to an appropriate course of education, one would obtain the adult brain. So that's the basic idea. Let's, as a model of learning, so learning is a loaded term. It means many different things in machine learning even. But let's take as particularly important the notion of learning as it happens through child development, and see if we can get some inspiration from that and insights into new techniques and paradigms. So so Turing wrote in 1950, in the last 70 years, our colleagues in psychology, child development, and so on, they have brought to us lots and lots of insights into how children's systems develop. So that's a huge literature, but let me pick just one paper, which is, I think, relevant to the task of 3D. This is an old paper that I picked, but its findings have held up, and there are many more papers which sort of support this sort of thesis. And this is a paper which says it's about the development of 3D. But I will read this line out, which is quite important. So there are 3 classes of cues that they consider. Kinetic cues, this would be like structure from motion kind of cues, right? So the optical flow, an object moves or the observer moves, and then you get multiple views. Binocular cues, which in humans is different than just generic structure from motion, because we have 2 eyes and we need to be able to solve the correspondence there. And then finally, of course, we have pictorial cues, which are available in a single image. So here are their key results. First, some sensitivity to kinetic information may be present at birth or soon thereafter. So they couldn't resolve this question, but basically they're arguing that the ability to do shape from motion may exist right at birth. Okay, so it's built in. The second is sensitivity to binocular information appears between 3 and 5 months. So at that stage, the kids are able to align their eyes properly and make use of the 2 images together. And sensitivity to static monocular information appears between 5 and 7 months of age. So these are fairly crisp and precise statements. So when I think about this in the context of computer vision, machine learning, AI, and so on, what this tells me is that using multiple views for recovering 3D comes early, that may be innate, may be partially tuned from experience. And then the ability to interpret structure in a single image, see 3D in a single image, so-called pictorial cues, comes later. And it's very reasonable to assume that this is learning and that this is bootstrapped on top of this basic capability. So that is, to me, a research agenda. So that's, what I'm going to state here is something I've believed in for decades practically, which is that my research goal is to develop the ability to 3Dify any image. And after we have had an opportunity to learn 3D models, and use the term 3D models in a very broad sense, some implicit 3D models, which are acquired from multiple views. Okay, so that's the research agenda. And I'm going to just show you a few of our results down this path. I'm not going to go into details. So this is a paper from like 5 years ago. So category specific object reconstruction from a single image. What we did in this was, I'm using this as a way to define what our interest is. We have a single image and I want to 3Dify it. And I still want to 3Dify any image from any place in the world. And that's the input, and this is the output. So we have now got these chairs have been 3Dified, and you see some kind of a depth map there. And okay, how do we achieve this? So there are going to be 2 stages. So there is a stage where we are working with a single view. So that's going to happen at test time. But then there's a learning phase in which you are allowed multiple views, because multiple views is the only honest, true signal for capturing 3D without sort of human supervision or supervision from LiDAR or various technical props. Okay, so how do we do that? Okay, so basically, I think you have to get to multiple views, and multiple views can be of two kinds. Okay, so there's an overview. So first learn category specific 3D models, and then we do 3D reconstruction of objects from a single image of a scene. So how do we do this? So basically, we can imagine two setups. One setup is what I call single instance, multiple views. So that's a classic SFM thing. So the reconstruction of the Colosseum of Rome is that example, right? From Noah Snavely. You have one view, one object, the Colosseum of Rome, and you have like zillions of tourists taking lots of pictures of it. Okay, here is a different setup. This is zillions of different cars. Everybody has uploaded one picture of it, okay, of their own car, so let's say. So these are multiple instances, single views. So the first setup was single instance, multiple views. This setup is multiple instances, single views. Now what's common to all of them is the category. They are all, so they share a family resemblance. And we are able to acquire models of some kind of a generic model of a car this way. And this is, of course, what we would dream about. And anyway, so we had some technology for this. We estimate cameras and then so on and so forth. And now the way we understand the shape is really as a mean shape and deformation modes. Okay, so that was 2015. Then we re-attacked this problem with Anju and Shubham and Alyosha. This was presented at ECCV. Now it's with tools of deep learning. But the broad setup is not too far apart. And here what we are doing is analysis by synthesis, but there are neural networks involved. So there is some image. We are learning these functions, which will reconstruct the shape, the camera, and texture. So there are some hints of intrinsic images here. And then once we have, and the training data is just lots of pictures of birds, not multiple views of the same bird, but single views of multiple birds. And then we can, once we have recovered these, then we recover meshes, and then we can render from novel viewpoints, etc., etc. Now, in that work, we needed to make use of key points. So the human annotation was A, this is a bird. B, this is the mask of the bird. C, these are key points like the tip of the beak, the neck, the legs, etc., etc. And finally, we have got rid of that assumption now. And that was a paper presented at this ECCV. So this is with Shubham Goel and Anju Kanazawa. And we've got rid of that. So that's what we are proud of, without key points. And it turned out that it needed an idea, which I think is an idea that many of you may find useful in many different settings, which is that how do the tricky part in this reconstruction, the initial at training time, when you're solving an optimization problem, is dealing with the camera. And if you just parameterize the camera in a standard way, just like it's, azimuth and elevation, then you get into trouble. You get into optimization trouble. And the secret is to maintain a distribution over lots of possible cameras. And this over parameterization, it turns out to be an effective way of avoiding getting stuck in bad local minima. It's similar to what happens with neural networks in general. Deep neural networks are over parameterized, and that prevents them from getting stuck in bad local minima. So again, the details are in the paper. But is this journey done? No, I think we have just we have got rid of key points. Is this technique like fully ready that I can claim any object category we have models for? No, we are not there yet, but this is our agenda. So hopefully over the next couple of years, we'll solve that. Once you have built your 3D models, okay? Once you have your 3D models and meshes, then what do you do? Okay, and this here is work with Georgia and Justin, which shows how a machinery for dealing with that. So this is the second part of the problem. Once you have models, then, and if you have a single input image, we can do 2D object recognition, and then we can reconstruct meshes. But this requires having those models in advance. And the first part that I talked about all the category specific reconstruction was really attempts to develop those models from multiple views. So I think this looks pretty promising. So I think that this is certainly quite doable. And I hear all the work which has been done using ShapeNet comes in handy. And here I would like to conclude by saying we have made lots and lots of progress in 3D vision, but there is a lot more which still needs to be done. Thank you very much.
Thank you so much, Jitendra, for a fantastic talk. So I see one question in the Q&A from Krishna Murthy. So the question is, one argument / proposition made early in the talk is that multi-view supervision is the most natural form of supervision. What's your take on multimodal representations, modalities other than vision alone, like audio, touch, etc.?
Oh, I fully support the use of multimodal. And I think that if I'd given a longer talk, I would have gone into other insights from child development, and children acquire information in a multimodal way. So that kid in the crib that I showed is playing with toys. So therefore it gets a shape from touch, hears sounds, sometimes even from, puts its lips on the object. So therefore there is that signal, interacts with the object. So we always have multimodality as well, and that should be utilized. So the secret is that the way we get rid of your classic supervised learning, so classic supervised learning with labels, which I think is kind of in its diminishing return stage. I mean, it led to a great deal of success for the field, but it's really in diminishing return stage. So how are we going to get out of it? It's some kind of self-supervision of some form, right? So therefore, and that self-supervision really comes from multiple views, multiple modalities, and so on and so forth.
Thank you, Jitendra. And yes, yeah, it relates nicely with a talk we heard yesterday from Christian Grauman, where she introduces audio into habitat platforms. So basically, an agent can learn both from multiple sensors. Another question from Abdullah Hamdi goes as follows. Nice talk. I want to ask, why do we care about single image reconstruction? We as humans perceive the world as videos, not images. Modern cameras can record videos and memory is not an issue anymore. Why images?
Okay, I'm going to do the following experiment, and everybody should do this. So I'm keeping my head still and I'm shutting one eye. I don't know, I see all of you still in 3D. I see all the objects in my room in 3D. Okay, we have this ability, we can do it. Okay, and we need this obviously for photographs, but we certainly have this ability, right? If I keep my head still and I shut one eye, the world does not disappear into flatness. When I go to a museum and look at a painting, the paintings evoke 3D in me. And it is all a continuum. See, when objects are far away, even in a scene which you are seeing in stereo, they are effectively flat for the stereo system, but it's because stereo accuracy goes with z squared. I mean, the error goes with z squared. So objects which are like 20 feet away, stereo is not effective. So when what you're doing at that stage, even in a real world scene, is basically relying on the monocular pictorial cues.
Thank you so much. I guess it's a good time to transfer. Okay, I think we can take one quick last question in the Q&A. So a question from Brent Griffin goes, thank you for your great talk. What are your views on using active perception on a physical agent in combination with this work? For example, a robot can collect many images from an environment to improve mesh models of a room.
And the answer is yes, that's a great idea. And this is why we have worked on systems like Habitat, which are active environments, simulation environments. And those enable us to study precisely these kinds of questions, because certainly human observers do this.
Okay, if I don't stop this now, there'll be an infinite amount of questions. So I'm going to thank you again for a really inspiring talk. You took us through a interesting time machine throughout very, very deep and inspiring concepts. So thank you again, Jitendra. And now I'll move the mic to Gordon to host our expert panel, where Jitendra will also participate. So Gordon, the stage is yours.
Well, thank you so much, Or. And I just wanted to thank all the speakers again of this workshop. I know this is a challenging time, and it's just great to see that everybody made it despite various challenges on internet connections, babies, and other distractions. So this was really a fantastic workshop. I also wanted to thank the organizers, of course, Srinath and Or, but also Tanner, Vincent, Shubham, and Leo. So I think this was a really great event that just touches up on a super hot topic right now. And so I've prepared a few questions for different panelists. We have a number of the speakers here with us right now, including Angela, Angju, Jitendra, Niloy, Noah, Tom's also here. I know that Angie has to leave at 11, so and I want to make this a little bit interactive. So I have questions, but you know, we can take questions from the audience. If you have questions or you would like something to be discussed, please just type that into the Q&A window here, and we'll monitor that. Okay. Okay, that's great. So maybe we'll just go ahead and get started then. And I'll start with a question to Jitendra, and all the other panelists are, of course, also welcome to chime in. And my question is this: I mean, I really liked how you presented this historic perspective also. I think, you know, some of the younger people in the community sometimes forget how much great work has already been done a long time ago. And actually Noah also showed this video from Andrew Lipman. That was great. Or the Paul Debevec's movie. That was actually something that inspired me when I was in my undergrad. So this idea of, you know, taking images and reconstructing underlying geometry, or this vision of, you know, inverse graphics, as you call it, basically, you know, it's been there for a long time, and people get really excited over and over in waves about it. And right now, I think we're at a stage where the pipeline has become somewhat differentiable, and we really have a true connection between the forward graphics part and the inverse graphics part in the same kind of a framework. But we're not quite there yet, right? You know, do you have any thoughts on what gets you excited about the most recent wave, other than photorealism, let's say, of these neural scene representations, neural rendering approaches? And, you know, what else does it take for us to get to the point where forward graphics is already with the inverse graphics?
No, I think that we are making good, steady progress. Okay, I think I like the work on differentiable rendering. I was very impressed by NERF. I think some of the ideas on sort of 3D representations with implicit functions and so on at every point, having a vector at every location. These are all very nice, good ideas. So I, as an old fogey, don't want to come across as, oh, we did all this 25 years ago. I think I do want the current generation to know that there were things we did long time ago, which they should be aware of, and not only just cite the papers from the last 3 years. Right? They should be aware of the classic literature, but there is very clear recent progress. So where I'm going is where I feel what is necessary is generality. I think, and we need to have less training data. See, I think humans are we have not really mastered generalization to the extent that I would like, right? I think humans have a very, very strong generalization ability for 3D. Our 3D system really works when I'm looking outside in my home. I mean, so this is sort of the view from San Francisco, from Berkeley, behind the fog. Okay, I can see the trees. I can reconstruct those. I can reconstruct objects in my home. I can reconstruct non-rigid objects like animals. And some of these I have had very little data on, right? I might have just one view of a zebra. So what's happening is a lot of transfer of this three-dimensional expertise across categories, right? And then the rules that have been inferred, like, I mean, we can do like the rules for stereo, structure from motion, shape from shading. Those have essentially got compiled into a form that they apply across domains, not just in the domain of the training set. Now, I don't think our techniques, our current generation of deep learning techniques have captured all of that. So the classical analytical formulations of shape from shading, they had a certain generality. They also had certain kludges because there were various assumptions that they made, which I think in the statistical approach, we don't have to worry about because we just let the data speak. So, but there are insights in those classical models which are not fully captured in our current machine learning systems. I don't believe that it's a matter of principle. I think that it could be done, but we are not there yet. And I expect it to take many years to get there.
Okay, fantastic. You know, I really like, personally, I'm super excited about the human visual system too. And I really liked how you described the depth cues. And I do agree that monocular depth cues are very strong cues. You know, one aspect that we haven't talked about much is occlusion, actually, because occlusion is generally considered actually the strongest pictorial depth cue. So shape from shading, stereo, other things are really great. But you know, is there something else that we can do in terms of occlusion? Is that something that we can use better? I mean, I think it's intrinsically captured by a lot of monocular depth estimators, but you know, I think it's.
So I think what's happening there is that there seems to be this disconnect between techniques which are focused on single objects versus techniques that are focused on scenes. So the techniques which are trying to capture spatial layout, like some of the earliest work from, you know, I don't know, Rob Fergus's group, like back in the, whatever, 5-6 years ago, those were capturing occlusion implicitly in some form. But I think that our current techniques, there seems to be a schism. Some people focus on objects and some people focus on scenes. And really, this should be one story, which I think is not quite there yet. And that would have the occlusion cue as a very key part of it, because that's the building block which goes between objects to scenes. And figure ground comes in right there.
Yeah. Okay, fantastic. Thank you so much for your thoughts. And okay, I know, Angie, you have to leave at about 11, so I just wanted to make sure to ask you something, which ties back actually to what Jitendra just said, is about, you know, I look out the window and, you know I can do it. I can reconstruct this 3D scene in my head, but, you know, maybe the computer, the algorithm or the network doesn't fully capture it. So, you know, one really exciting aspect of some of these learned 3D representations is that you can connect not just the shapes and appearance, but also the semantics, right? And so thinking about how a representation can capture all of these aspects together, so you can do inference with partial data and for the model to learn just more about it than just very basic geometric shapes. I think that's very exciting. And this is also an area that you've done a lot of work on in the past. You know, so I was just curious if you have any thoughts on, you know, how to connect semantics and the structure together in how do we capture that in a representation in a meaningful way?
That's a good question. I mean, I think we're still a bit in the early stages of figuring out, you know, what are the right 3D representations and for which tasks that you care about in particular. Because I think it probably does depend a bit on what kind of downstream tasks you're looking at. I mean, in terms of semantics and geometry and appearance, I think a sort of natural representation that people kind of probably think about is still decomposed into a hierarchy of sorts. Like a scene is actually composed of a set of objects. Whether to represent every part of that specifically in this kind of graph, like a scene graph, I'm not sure what exactly is the right representation there. I think the kind of nice thing about really predicting low-level things like geometry is that it does seem to actually help a lot in terms of these sort of higher level tasks where we want to pull together these kind of geometric features to figure out what all the objects are. And I think that's kind of nice about having actually this very low level geometry prediction task, that in fact it helps to learn across these kinds of different views the same kind of objects, which is kind of cool. But I think there's a lot to be explored in terms of like basically how to combine together so this kind of object-based, scene graph-based kind of representation, which actually I think some people here have done some work on a bit more than I have. In this kind of inference from, let's say, like an image being able to predict basically the geometric representation of the scene, as well as each individual object, how to interact with that object, what the occluders are, and to combine that together, that seems like a nice way to go. Hopefully without too much engineering for each individual part within that framework.
So just following up on some of the things you said about what's the right representation, you know, there's a lot of thought on, you know, we want to have a disentangled representation that disentangles all the different parts, because that's great, because then, you know, the network probably has an easier time to learn meaningful things that are structurally sensible. But, you know, at the same time, we're taking away some freedom of having it learn some internal representation that does capture things that, you know, we can't explicitly model directly. So do you have any thoughts on, what do we want everything to be entangled or disentangled, or how much entanglement do we actually want?
I'm not sure what the right answer is here, but I kind of like this kind of base geometric representation that is not necessarily strictly tied to every individual object or so. I think that's also like people can perceive depth relatively well up to some coarse approximation. Like Jitendra mentioned, you like cover one eye, you can get a very good approximate depth up until somebody hits like a tennis ball at you, then you're a bit screwed. But I think that seems to be kind of a good lower level cue that seems to be also shared across, I think, a lot of higher level semantics that you can infer from it. So it would be kind of nice to also have this combination of the two. But we're still, I think, working a bit towards what works best in this regard.
Okay, fantastic. I think Noah wants to jump in here.
Yeah. So first of all, I just want to say, well, this is great to be here and hear all these great talks. I also may have to leave early, so in case you see me mysteriously disappear, like I'm not in a black hole. I just probably had to go take care of kids. But I'm really actually interested in these questions of like, I don't know, computer graphics, inverse rendering, like that has come up in the last few questions. Like, I do think that this like, well, okay, I think different of us here came at computer vision from different angles. So like at some level, I'm a computer graphics person at heart. I don't care about robots that can perceive the world as much as I care about like creating beautiful 3D models of the world. And you see this kind of graphics and vision, I guess, tension, I don't know how to call it, but like playing out in different ways. Like, some people say SIGGRAPH is dying and like CVPR is all where all the cool stuff is happening. But I really do feel like this is like where it's at right now, like this adopting of computer graphics methods and ideas in computer vision, whether it's for like reconstruction and creating compelling visual models, or for like more perception-based tasks. And I think it's like, I don't know, I feel like computer graphics has been kind of optimizing for a certain kind of pipeline, like, with meshes, everything is a mesh and a triangle, and everything is like texture maps. And Angie's been doing great work with meshes, and maybe meshes will win. But I think like somehow this, addressing this tension by combining, these graphics pipelines with learning in the right way seems like the super interesting problem to me right now. And
I mean, you call it tension, but to some extent it's also there can be a better synergy. Let's call it, there's an opportunity also, right? Because the graphics community has spent decades on engineering these really great pipelines that work just super well, and they're optimized for certain tasks, for the forward rendering task mostly, right? Not so much for the invertibility. But even there, we've seen over the last few years a lot of differentiability coming into these high-end renderers, even offline rendering, right? Monte Carlo sampling, and I think Mitsuba 2 even is fully differentiable now, and so on. So I think there's an opportunity also to learn from these structures to bring more of an inductive bias into the network architectures that we're developing in the computer vision community, but also, of course, for the computer graphics community to learn from the computer vision community and how to learn things that are, just difficult to model explicitly. So I think, whatever could be a challenge can also be an opportunity. So I think it's great to see actually a number of senior people from the graphics community and the vision community come together in this workshop. And I think that's just really a good starting point also to have this conversation. Okay, actually, no, I was just so blown away when I saw your, building Rome in a day work back in the day. Jitendra also showed it again just in his talk now. And, this idea of city scale or even global scale reconstruction, that it's just, something that is hard to grasp. And you've done it kind of with a lot of your work back then. So now in light of neural rendering and a lot of these techniques, we've seen, of course, Nerve in the wild, a lot of your work that you showed earlier also, it's moving towards this large scale reconstruction of view synthesis, but we're not quite there yet, right? Is there anything specific where you think, oh my God, like there's this one core challenge that we need to solve in order to just be able to scale it up to that dimension, or?
Yeah, I mean, this kind of thing does keep me up at night. So, I mean, I think there's a sort of prosaic challenges and kind of grander challenges. I think there's a prosaic challenge of just like, I think if you wanted to take NERF and apply it to Rome, it wouldn't work because it's too big and it doesn't scale, and it's maybe you could just break up Rome into little blocks and fit NERFs to it. It's not clear, and if you also want to capture like materials, and it's not clear that that will scale. So I think there's a question there of just like scalability. The reason I like this work, as I sort of highlighted in my talk, or I want to recreate what it's really like to be there. And so the big thing that I feel like is, it's not enough to just reconstruct the Colosseum and all the other landmarks and just like be there in an empty ghost town. You have to have audio, like it has to sound right. There have to be like, if you sort of close your eyes and imagine sitting in the cafe across from the Pantheon, like you can kind of imagine all of the things that are missing right now. The tourists milling by, the like, I don't know, smell of the coffee, espresso, whatever. So I think those kinds of, first of all, the multimodality, like audio, but also just the dynamism of, all of those things that are not captured by static reconstruction. That's kind of the biggest challenge I see.
Yeah. That's a really good point. We've seen a lot of really impressive work on recovering static scenes, but the dynamics are somewhat missing still. And the smell too, of course. Although I don't know if I want to reconstruct the smell of the wildfires that are burning through the Bay Area.
Yeah.
Okay, this is fantastic. So I think you mentioned also just Angju's work right now. So maybe I'll switch over to a question to her. We've seen a lot of great progress on, low dimensional parametric representations of geometry. And then we've seen implicit surfaces coming up again. Like these are all, to some extent, also traditional representations that people in the early days of the graphics world have played around with quite a bit. And, meshes have become the dominant representation there. But it seems like right now, is up for grabs again, which representation is the best. Do you have any thoughts on, parametric versus implicit representations or any kind of other representations and what their relative benefits and disadvantages are? Because it seems like a zoo out there right now, again, where everything goes. And, it's good to just discuss what really the benefits and disadvantages of these different representations are.
Right. Well, first of all, I think parametric and implicit or not actually they're not opposing forces actually. So I discussed in my talk, there's this talk, we did this bird work, and that was all in meshes, but Shubham has a recent paper that just made it into implicit functions. But then I think parametric and non-parametric, I think there's a very big difference. So for example, in humans, for parametric models, we use simple body models. And then more recently, we had an implicit function-based volumetric reconstruction that can do front and the back, including a texture. It looks really good. It's called PyFu. And that one's like fully convolutional implicit functions. And that one is able to capture real fine details like skirts that would be really difficult to capture in a parametric model. At the same time, once you get that, there isn't that much of a high level, or there's no correspondences or low level control or the kinematics parameters that you might want to use it for your end task. But then I really think it's the two things that's going on, which I don't think is really opposing, because I kind of came from this computer vision type kind of direction where I wanted to capture the underlying state in a low dimensional manner so you could use that for some other task and so forth. But then I recently worked with Noah because I visited Noah's lab for a year at Google, and it really did inspire me and really changed the other direction of why this is really important, which is like this ability to capture the world. And it really has a lot of big, impact in like the kind of stories that you can tell when you are capturing. And then there's a really cool recent article from New York Times that really does this, and they go to a hurricane place and have like a drone, and then you get to see the experience. And I think that's really impactful too in two different ways. And both of these draws attention, inspirations. But yeah, I think non-parametric can capture a lot more, but then you lose a lot more correspondences, which you may want to do for all of these other higher level tasks. Higher level tasks don't tend to capture that much detail, but actually these are all coming together. And then now there's the PyFu one and the simple one, and there's a new work that's in between from FRL, from Tony Tang and Christoph Lassner's lab called Arch. And I think Yebin has another paper called Pamir, which combines simple and then just defines the implicit function on top of it. So maybe we can actually do both. So I think it's a really interesting time, and yeah, it seems like everything is merging. So I think that's kind of nice, or not everything, but hopefully it goes in that direction.
Sure, and the parametric surfaces also allow you to edit things, right? Like editability is something we haven't really talked about much.
Yeah, deformation. Yeah, deforming. Yeah.
Okay, so there's actually a question from the attendees, also from Jan, is asking, most learning methods focus on single objects or indoor scenes. What do we need to get these methods to work in a world setting? And I think that ties back to my question earlier. Maybe that's for you and for Noah also. Again, what's the right representation if we actually want to scale? If we want to think about scaling it from one object to an entire city, are parametric shapes the right thing? Point clouds, implicit functions, what's the way to go?
So this I want to pass to Jitendra, but we also have this recent work at ECCV where we reconstruct people and objects from Coco images. And I want to pass to Jitendra because I think this is really where objectness prior is coming from. And so if you wanted to recover a scene with lots of components, why not model at the object level? You can use the model the objects in whatever representations you like, and then learn to compose them. I think that's
Right, and so this is actually a great transition to my next question also, maybe for Tom. So Tom, you've recently worked on this idea of compositionality, basically composing multiple different implicit functions that are locally defined, and that's just an idea that really makes sense. I hope you're here. Actually, yes, you are.
Yes,
here.
I am.
Okay, it just makes sense from a conceptual level, right? And then, but over the last couple of months, and we've seen a lot of work also on things like NERF that actually also achieve photorealism on pretty complicated scenes. So, what are your thoughts on this? I think this compositionality aspect. How do we get this into all of these models somehow? Because it just seems like something that is a critical component in just scaling things up. Whether you have a photorealistic neural renderer, or whether you have even a more expressive implicit representation, I think compositionality is something that you need in any case.
Right, exactly. Yeah, I think this relates to several of the previous questions too. For me, the most interesting thing is the analysis task of extracting structure from observation, which is right at the heart of your question, which maybe if only you want to visualize, you only want to produce new views, and they need to be photorealistic, that may or may not be important depending on the size of the scale of the thing you're trying to visualize. But if you want to interact with it or edit it or any other task besides visualization, then I think that's the hard part. I think it's the interesting part. And for many applications, it's the only part. Like I don't really care if I can resynthesize a new view. I really care if I can interact with it, or I can, relate. How does this shape relate to other shapes, or materials, or whatever. And so I think this extracting structure is like the most interesting part of the problem, and that is critical for representing scenes or cities or anything else, so that you can decompose it into parts that are easy to learn because they're highly repeatable across many instances.
Yeah. And so when we think about, let's say, editability, again, it's a topic that we haven't talked about much. It's really important in graphics, where you not only represent a scene and render it, but you also want to, edit it, because that's how you tell stories and so on. For computer vision, mostly we think about, okay, we have an image or a video and we want to reconstruct it. But I think this editability has also become more and more important, I think. So do you have any thoughts on how to bring that into this whole discussion on not just the scalability, but also editability?
Yeah, I guess editability is mapping observation to parameters that people understand and can control. I guess that's what that is. And again, I think that's an analysis task. I'm not sure I have anything smarter to say than that. You could explicitly do that. We have a project that we've done where we try to define semantic parameters and then learn those and then allow people to edit them. But that's very you figured out the parameters, the attributes in advance that you want to modify. I guess you can, through self-supervision or unsupervision, extract parameters that seem to cover the variation, but who knows if they're the ones that people actually want to modify. I don't really have anything incredibly smart to say about this, other than I think that extracting structure isn't only about editing. I think it's mostly about what can you do with it other than a human editing it, by turning knobs. Mostly about reasoning about what will happen if, what's likely to be the function of that thing. Those are the kinds of questions that aren't about editing that I think are the most interesting.
Okay, but going back to this scalability issue, that's also more closely related maybe to your work, is do you think it's better to, think about chopping up the scene into small bits and do this not only object level representation, as Andrew was saying, but actually part level representation, right? Or is it, object level representation, or is it, global representation, or could there be a mix of all of these too, also at some stage, some kind of a
something that's if you took inspiration from how people represent cities now, or large scene graphs or games or whatever, some hierarchy makes sense, and at the finest level it should be something that is where there should be a strong prior to what the data within that component is. Maybe at every level there should be a strong prior with regards to how it relates to its parent and its children. And so the key is, how do we decompose scenes where that's true?
Exactly.
So they're easy to learn. Yeah.
Yeah. Okay. Fantastic.
Okay. I wanted to jump in and make a remark, which is that compositionality is sort of that's what a computer scientist loves, right? Because this is the way to collapse exponential spaces into linear growth. So, so compositionality for us comes in various different ways. Into different objects, or splitting up into geometry plus albedo plus lighting, etc. These are all different ways of bringing in compositionality. And I think that we have to have it. This is the only way to get scalability. On the other hand, there are certain settings where we may leave things unfactored, leave views unfactored. So think of rendering a butterfly's wings, or the appearance of an old style CD, right? These are cases where the BRDFs are horribly complicated, right? So all we may have is actually just a bunch of appearances and just leave it at the light field stage and don't factor it. So I think compositionality in most cases is desirable, but there may be settings where we do not bother.
Okay.
Can I add something to that? Because I think in a panel, it's good to maybe also voice other views. So we have been talking about disentanglement, but I would like to say we can also think about the same things from the control side. So we want not necessarily a disentangled representation, as the presenter said in certain sense, but we definitely would like to have disentangled control, that the user can probe the world in a control setting. I want to move the objects. I want to maybe change the appearance or copy the appearance, copy the style. And in the blog can and the relate work that I presented, we tried to do that from the user point of view.
Okay, so actually my next question is for you. I'm particularly happy to have you here in this workshop because I think, just having a little bit more representation from the graphics community is, I think, good because there's been just so much work in that community that can be directly applicable here. And, you've spent a lot of your career thinking about representations and how to represent shapes and geometry and so on. And, among all the different choices that, traditional graphics has to offer, including meshes, parametric surfaces, point clouds, implicit surfaces. Right now, it seems like people are just trying to apply this to these computer vision problems in different ways. And I think it goes back to the question that I asked Andrew also, in your, expert opinion, which of these representations are most important? And maybe right now there's a big focus on parametric, voxel-based representation, point clouds, all of these, but are there other representations that we haven't really looked at in the computer vision community that, are maybe used in the graphics community or maybe have been abandoned in the past also?
This is a topic we teach in the geometry processing course about the different representation and what are the pros and cons. And so far, even though we have worked on it 20, 30 years, there's plus and minus in each column. There's no clear winner. I think the power of any method lies in how easy is it to transition from one to another without losing information. And that's what these unified representations are giving us. Right? And now we have yet another representation like these deep representations that are not explicitly where the power is. We don't explicitly factor out maybe the geometry or the material, but we keep it as a learned renderer. And I think that has some advantage. The power of such a method would be if we can enable the same sort of control, as I mentioned again, from the user perspective. But that's what's really important. And if we talk about scalability, then maybe hash tables are better. If we talk about fast implementation, voxels are better. If we talk about having a global information of the region, then SDF is better. So there is no clear winner. And I think even 10 years down the line, we will be still going plus and minus. Some representation will be popular for a few years, and then we will move on to something else. But I would say it's not just which is the winner, but having the agility to move quickly from one to another and having it end-to-end differentiable. That would be the benefit.
Fantastic. Okay, so here's a question from Jan also, and this is maybe for you and also the other panelists is, I think it's related to this, graphics community having created really efficient tool chains over the last decades, basically. And in computer vision, we're just maybe seeing those emerging with, maybe PyTorch 3D or other kinds of tool sets. But, what are we missing so that people can easily get started in this topic of 3D and multi-view, let me call it inverse graphics? I'd say there are a few tools already emerging, right? Yeah. But is there a better effort maybe that we can do as a community to, unify and make it easy to explore this difficult space, let's say, of all these different representations?
Well, there's now Mitsuba version 2 that's differentiable. So that's like a start, but then there's like all kinds of, Unity. When will that be differentiable? For example. So we have a long way to go from how people describe scenes and render them in dynamic settings to differentiating back to learned features. Those tools don't exist.
Yeah. I mean, I think the community has been pretty good about releasing code, and I know Vladlen's lab also has Open3D. I forget what the name of the library was, but also this effort to kind of, I think that's more for multi-view and in the 3D space. So hopefully those directions are coming. But yeah, perhaps I think maybe there's lots of interest, and I started teaching for the first time this semester, and I'm teaching a seminar on learning for 3D vision. And so in doing so, I had to put a curriculum together. So maybe that would, help me put things together in one box, and, that could be a resource maybe.
Maybe one thing that prevents plug and play right now that came up in a couple of discussion is, as Jitendra mentioned, we have made a lot of progress because of ShapeNet, which means that many of the methods are class specific. And then when we take an image of the room, like the scene behind you, Gordon, I will have a very tough time modeling the lamp. And then what to do? And that's I think where we have to make progress in this rare objects or not so popular objects, let's say.
Yeah, okay, we'll get back to that in a second. Like, I want to ask a question, or maybe more like a comment that ties back also to something that Jitendra said earlier, and that is this question of generalizability. So we've seen a ton of papers recently on single object or single scene overfitting. Given a couple of images of one scene, we can interpolate or extrapolate the views. But to some extent, in my understanding, one of the most powerful things of these differentiable representations is that you can learn this generalization across objects, across classes, from ideally not 3D shape repositories, but from natural images, which requires you to have a neural renderer on top of it. But this generalization aspect seems like, one of the really mission critical pieces of this entire effort across the community. So, but oftentimes it's just mentioned in passing in the papers, or, people use, okay, we're going to use a convolutional encoder, or do some kind of conditioning by concatenation. A few people like Vincent have been exploring hypernetworks more, or in most recent work also meta learning. But I think there's many open questions on how to do this generalization, and it ties back to what representation you're using, of course. But I'm just curious, and this is maybe more of an open-ended question, is like, what do people think about generalization? How do we approach this even?
I mean, for me, it goes back a little bit to compositionality. So like the lamp that Nilay mentioned that's behind you, Gordon, I've never seen that lamp before, but I've seen parts of lamps. I understand what a glass shade looks like, and that the top of it looks like a upward facing glass shade, or whatever the right word is for that. And so I can make out of the parts of the lamp, a description in my head of what that is and what its parts are and how they go together. So I think compositionality is a big way to help get generalizability. Yeah, I want to say one more thing that's kind of relevant to that, but not really. Jitendra brought up the example of seeing a zebra. Like you've never seen a zebra in your life. Maybe you've never even seen any animal like it in your life, but you still can make sense of, from a single photo in a book, what the 3D shape is. And that's a different kind of generalizability, because it's like interpolation between four-legged animals you've seen before, not extrapolation outside your space of anything you've ever seen. And there's two different kinds of generalizability, I would say. Anyway.
Yeah.
So, okay.
Sorry to interrupt. Yeah. So I wanted to make one remark about how we get out of where we are to this generalizability. So I think generalizability is our challenge. We really need to be studying this. And I think, to me, one very practical thing we should be doing here is data sets. So data sets in the computer vision community, we've gone through these various stages, right? So for object detection, there used to be Pascal, and then there was, there was Caltech 101, then there was Pascal, then there was the ImageNet and COCO. And that the evolution of data sets made a very big difference. Okay, I think that we really need real world data sets. ShapeNet is, in my view, is not a real world data set. I think that, so ShapeNet, it feels like a Gen 1, first generation kind of data set. We need our second generation data sets, and at some point we need like a third generation data sets. And now, of course, we can take pictures. So we can get lots of multiple views. So since I've been arguing multiple views, okay, we can obviously take multiple views, and there are data sets for that. But what we don't have is matched ground truth for that. So if I have multiple views and then I do some reconstruction and I want to write a paper on that, well, how do I prove that that approach is good, right? So we had this problem in the birds work with Anju. Okay, how do we sell people that this reconstruction is good? And you're left with various sort of not totally satisfactory techniques. And if you have not very satisfactory technique, referee 2 comes and kills you. So I feel that we will need to have some data sets which are multiple view in nature, but which have some degree of ground truth, which will enable the community to get off the crutch of ShapeNet. And I think that will, and the richer they are, I think that will force us to study the generalization questions.
Right, but it goes back to, we can use computer graphics to generate the views, and then we have the ground truth, but then it's not necessarily representative of the real world. But if we have real world images, we don't necessarily have the ground truth, or it's noisy or corrupted. How do we break that cycle even with a data set like this? I think, it's not as easy as doing like a crowdsourcing labeling kind of a task of like a bunch of multi-view data sets, right? I think we have seen some efforts, but what do we need here?
This is the reason why it's not been solved, right? It's 2020 and we don't have it yet. I think it can be done. I think we just have to prioritize it sufficiently. Look, physicists spent 40 years setting up experiments to measure gravitational waves, right? I think once our field gets in the direction that something is necessary and it's going to be tedious and a big effort, but we have to do it, we have to do it. So I think for a few years, we were perfectly happy using ShapeNet, and given where our techniques were, we could develop stuff in that paradigm. But we are, I think, beyond that stage now. Sorry, I interrupted Niloy. Yeah.
Yeah, so I wanted to say something that's of a concern to me, which is about this data set that Jitendra mentioned. So that's two aspects. One is a single object data set that we can collect, right? And ideally with 3D. But if I go back to your to the scene behind Gordon, there's several interesting things happening. And Gordon, sorry for picking up on the background.
Okay.
So for example, the lamp is not functionally a lamp now. It's not on the floor lamp that we're looking at. We don't even see anything that tells us where the floor is. But I have this hypothesis that we do a lot of even recognition in terms of context. I see you, and I know you're a human, you have a certain size. In your case, I know your height also. I know the table, I can guess the camera. I know where the floor is, and I imagine, given the location and the room, that's likely to be a lamp. That's how it is, right? Now, you talked about synthetic data being generated, which we can do very well in graphics. And the scenes we have done so far is, here's a room that we model by some random box, and we throw in some objects, and that becomes a scene, but that's not in real life. And I am not aware of any real data set or even synthetic data set where the code distribution of objects, their statistics, is reflecting real world statistics in terms of relative depth, etc. Maybe Tom has something to say. And I think that has a limitation, that whatever we do, this type of clues, if that's a useful clue, we are missing out in exploiting.
Maybe there's a way to learn again, like bit by bit. So if we learned let's say hypothetically ShapeNet were more realistic than it was and covered every object in the world. maybe we can learn about objects from one data set, and then we learn about composition of objects into small groups of objects from some other data set that doesn't need to actually have all the 3D shapes and all the materials and all the everything else. And then we learn about rooms from another and cities from another and so on and so forth. And so we didn't really need a detailed three-dimensional model with all the materials and all the lighting and everything for the entire city to learn it. So maybe there's a way we can learn it bit by bit.
Yeah. Yeah. These are all very good points. So I just took some notes on, what came up as maybe some of the most important things that we need in this community, and I'll just read them to you, and then maybe you can disagree or agree or add a few other things that we need. So I have this question of compositionality as one of the key aspects that we somehow need to understand better. I have generalization as something that's closely connected that we need to model better. I have neural rendering as something that could enable the 2D supervision, right? Which seems to be a key to moving towards away from the 3D supervision of, CAD type data towards natural images. And then I have the data sets as something that we can use to learn priors, but also as a pragmatic thing, because reviewers want to see quantitative evaluations, and unless we have ground truth, we can't deliver them, and ideally have that in a standardized way. Is that capturing about like some of the most critical pieces that we need as a small community, or am I missing something here?
Maybe the unsupervised part. That's
the unsupervised, I think that's what I was trying to capture with this neural rendering. Maybe it's like moving from strong 3D supervision towards maybe 2D supervision towards somewhere where we can really supervise with natural data, where we have just an abundance of unlabeled natural images, and bridging that gap somehow. I think the neural rendering is basically a core component in that, but maybe it's not everything that we need. So maybe I'll just make that.
No, I would argue that actually the 3D computer vision community has done a better job of moving towards weakly supervised or self-supervised than the mainstream computer vision community. In the mainstream computer vision community, full supervision still reigns supreme. The unsupervised techniques are used as some kind of pre-training, but basically they're of dubious value. They give you like 1%. Whereas in our community, the fraction of papers which are using supervision from multiple views is, I would say, the larger fraction now. So I think actually that the 3D computer vision community has in fact done a pretty good job of showing by real work, real research, real papers, the power of this. So that's one remark I wanted to make. A second remark, which is also meant to be like a pat on our own back, which is that when the deep learning craze started 5 years ago, I was very concerned whether it meant the death of all our classical knowledge. All those clever insights we had about perspective projection and the physics of light and optics and so on, was all of that going to be forgotten? And we would raise a generation of ignoramuses who knew how to use TensorFlow and PyTorch, but didn't know any of the mathematics of perspective projection. And I think here's good news. I think that the latest developments that we have, I mean, I'll pick NERF, for example. This kind of a paper can only be written by people who understand something about light fields. Okay, so it's great. I think we should all pat ourselves on the back, because what we have shown is that to do advances in this field, at least in this corner of computer vision, we have to bring in insights from about geometry, optics, rendering, physics of light, and we bring in insights from sort of learning and generalization with all the differentiable rendering and this and that. So we have actually unified this. So if I'm in a debate with somebody who's like a pure learning fundamentalist, I will always use examples from work in this area as an indicator that classical knowledge is still valuable.
Yeah, that's a very good point. I mean, I think that was a big concern for many people, that we're just going to train neural networks without even understanding what they do. But this convergence, I think, of, I sometimes call it physics and AI in a meaningful way. How do you combine these two things, or the knowledge that we really have, that we have built up, not just in the computer vision world, but this applies to, I think, all disciplines where AI is being used. I mean, I work at the intersection of optics and AI a lot, and we don't just want to throw away Maxwell's equations or a lot of the knowledge that we have. We want to use it and combine it so that we can use the best of both worlds, like model the things that we can model with the tools, with the knowledge that we have, but learn the parts that we don't know, right? So I think that's a very important point. Any other thoughts on big challenges?
Yeah, there's one thing I want to add to the list of challenges, which is really something that came up in the past that Noah mentioned, but this aspect of non-rigidity and dynamicness. I think we live in a world that is 3D and also dynamic. So there's lots of non-rigid objects. And even if it wasn't humans or animals, things move around once you interact with them. And so I really think in this regard, we need to consider more about video and the dynamic nature. And one thing I want to say is that I'm all for multi-view because we have a head camera that we move around, but I'm not so sure about simultaneous multi-view. I think that's a very good setup to capture data, but I don't think that is very ecological. We don't have an omnipresence kind of eye everywhere looking at the same thing at the same time. So I would say video in particular, if you're only thinking about static objects, video and multi-view is kind of similar. But I think if you think about the dynamic nature of the world, video means something very different from simultaneous multi-view setup. And I think making that distinction and also having models that I think it tends to be like, if there's a single object-based model, it would be like, I'll take a single image and I'll give you some 3D. And then if there's more images, it should get better. I think Jitendra has a work with Abhishek called Learning Stereo Machines. I really like that work because it's designed so that when you get more information, your thing updates. I think we need to kind of go a little bit more in that direction also. And there really video is key in dynamics.
I would like to riff off of that. The thing I was going to say was about lifelong learning and online inference and things like that. So if you have an internet collection of observations that are completely one-offs, unrelated to each other, then it makes sense to do the kind of work that we do. But almost every case where you have a camera that's trying to infer 3D and do something with it, a robot or a self-driving car or a surveillance system, you pick your favorite thing. It's a camera that's operating inside an environment, and probably it's the same environment every day. And so the idea that we're going to drop from Mars to have to figure out the scene and then forget it, this isn't a real thing except it's for internet collections. And so I think this like lifelong learning and persistence in our understanding of what we're seeing is something we're completely missing in the computer vision community. Obviously robotics people think about that, but in CVPR kind of, or ECCV kinds of settings, it's very rare people talk about that.
Okay, so what do you think is necessary to achieve that? When we think about representations, for example, like a representation that can be updated somehow?
Yeah,
or?
exactly. So we had a paper at ECCV last fall where we talked about inductive instance segmentation. So rather than the problem being from observation to instance segmentation, the problem was from your model that you had from observing the same place in the past plus an observation to an update to the model. So let's just say that that model is an instance segmentation. So you've been in the same place before. Things have moved, everything's different, but you are starting from what you knew before plus your observation, and now you're trying to update what you know. And I think that's the real task for most computer vision systems that operate in the world. Not you drop from Mars, make an observation, have to figure it out from scratch.
Yeah. That's a very good point. Yeah. Any other thoughts from other panelists? Okay, so then just to summarize that again, I think what we discussed as some of the key challenges for this community as takeaway messages are, things like compositionality, generalization, modeling dynamics, also something that we haven't seen too much. Thinking about how to get towards unsupervised learning, and neural rendering goes from 3D to 2D, but kind of need to think about that in a more nuanced way. For example, Angju's work on, looking at single views of multiple different objects or single views of the same object, for example, in a video. I think thinking about how to get the supervision to work with data that we just have more of, rather than multiple views of the same object. I think that's very important. Dynamic updates of a representation. So when we come back, we want to update it as we get more data. It should get better. Something we haven't seen too much in this community. And then of course these data sets that not only allow us to learn things, but also to evaluate things so we can get our papers accepted, just as a pragmatic thing. So I think these are some really good takeaway messages, and maybe we can just send an email to everybody with the summary of the panel, or get this to people in some other way. So I know we're running quite late and people probably have other meetings already set up. So I just wanted to thank all the panelists again, the speakers, all the speakers, the organizers, and of course the attendees also for sticking with us. This is really a really exciting topic, and I'm particularly glad to see this convergence of graphics and vision, because for me, graphics and vision were always the inverses of one another, although I've been more in the graphics community. It's really exciting to see this convergence, and also, of course, the message that we don't just want to blindly learn everything. We want to build knowledge and bake that into our architectures, and have our representations use the knowledge that we've built up as humans, and not just learn everything from scratch. I think that's really important takeaway messages also. And maybe it's easier in this community because there is so much structure that we can learn about than for other computer vision or machine learning tasks. So with this, I'll hand back over to Or and Srinath for any concluding remarks that they want to make. And I'd like to thank you for sticking with us.
Thank you, Gordon.
Thank you.
Thank you. Bye.
Thanks everyone. Thanks Gordon.
Everyone. Thank you for the organizers.
Yeah. Thanks.
Thank you all for joining.
Just a final concluding remark. So if someone wants to hang around in the gather.town interface that we have for the workshop, we might have a post-workshop social, just as we had in session 1. So please feel free to stop by and
Did you add a virtual bar for the post workshop session?
I think Or should know more about if he had added a virtual bar.
I can actually quickly set up one.
Yeah, we have lots of areas to hang out.
Yeah, let me quickly set up a bar so we could meet at the bar. I will update that. And I also wanted to mention that all talks were recorded. So, and also the panel. And the panel, I think, was fascinating. Gordon, thanks a lot. You did an amazing job, and the discussions were fantastic.
Okay, great. Thanks, everyone. And I'll see you at the virtual bar, hopefully.
Thank you, everyone. See you.